Education and technology will enable all to participate fully in the wonders and benefits of American life. One area where those wonders and benefits is most apparent is space. It's long been a goal of our space shuttle, the program to someday carry citizen passengers into space. Until now, we hadn't decided who the first citizen passenger would be. But today I'm directing NASA to begin a search in all of our elementary and secondary schools and to choose as the first citizen passenger in the history of our space program, one of America's finest, a teacher. Now, I promise you there'll be a little bit of volunteerism in that also. But when that shuttle lifts off, all of America will be reminded of the crucial role that teachers and education play in the life of our nation. I can't think of a better lesson for our children and our country.
Everyone flown aboard NASA spacecraft until this point had been chosen for their technical expertise. For the first time, they would be starting a search for a civilian to send to space. Someone whose primary title was not an astronaut nor an engineer, but a teacher. Someone who could describe the experience of spaceflight to every classroom in the nation. Allowing the opportunity for a member of the public to join a space shuttle mission, as well as that being a teacher, would be a major effort to help spur public interest in the program. NASA releases an announcement of opportunity outlining the requirements for applicants. From all over the country, over 11,000 applications were received by NASA. Each of the states and territories chose 2 teachers each, narrowing the selection down to 114. These 114 meet with President Reagan in the White House, where he gives a speech to those teachers.
First, let me congratulate you all. The fact that you've come this far in the selection process is testimony to your abilities and the respect of your colleagues, and I'm sure that you've made your schools and communities and your students very proud. I also want to tell you that your shuttle doesn't blast off for a while yet, so there's still time to back out. I suppose that we all have a few special teachers that we remember with particular affection and gratitude. One such teacher for me was Esther Barton back in Dixon, Illinois. I sometimes wonder what she would have made of our Teacher in Space project. And I have a hunch, remembering some of my escapades, that if she were here today, she'd tell you this won't be the first time I've sent a teacher into orbit. I'm glad it's not me who will have to make the final selection of the first teacher astronaut, because each one of you is eminently qualified. For the lucky one who does go up in the shuttle, I have only one assignment. Take notes. There'll be a quiz after you land. So I got to get back to the Oval Office. Thanks very much.
A review panel meets with each of the remaining applicants and narrows the selection down to 10 finalists. These 10 finalists undergo extensive physiological and medical evaluations to make sure that they're ready for the stresses of spaceflight. The selection process would finalize in Washington, D.C. after interviews from NASA officials with each of the teachers. The committee found the recommendation for the primary and backup teachers that will be receiving spaceflight training and be flown on the mission. The finalists all gather in the White House for NASA Administrator James Baggs and Vice President George Bush to announce the teacher that will be flown on the mission, as well as the backup that will also receive training.
Given that this is such an extraordinary group, it was not easy to decide who gets to fly in the shuttle next January. Our final decision was based on who best met the criteria we laid out at the beginning: originality and creativity, dedication to the teaching profession, a high degree of community involvement, and an ability to communicate the spaceflight experience. We aim to keep our winner and backup candidate very busy in the coming months, training for the flight. But we also will ask the other 8 finalists to get involved in the space program as well, mainly because we think they're all too good to let them get away. Over the coming weeks, we'll use their talents to help design lessons and demonstrations on spaceflight to be conducted by the winning candidate aboard the shuttle next January. Some will be broadcast live, others will be filmed, but all will be shown in classrooms throughout America. With it, we hope to communicate to the millions of young people throughout America some of the wonders and mysteries of spaceflight. We also hope to strengthen our ties to the educational community to ensure that our high adventure in space will continue to inspire young people everywhere. Over the past few weeks, our 10 finalists have lived and worked together. They've endured exhaustive and really extensive mental and physical tests and a battery of interviews. They've been interviewed more times than you can imagine. And just as we have gotten to know them inside out, so they have gotten to know each other as well. Now I have the honor and privilege to introduce to you the Vice President of the United States, Mr. George Bush, who will announce our winners.
Kind sir. Well, we're here today to announce the first private citizen passenger in the history of spaceflight. So let me tell you now who our teacher in space will be, and let me say, I thought I was a world traveler, but this tops anything I've tried. And first, the backup teacher who will make the flight if the winner can't, Barbara Morgan of the McCall Donnelly Elementary School in McCall, Idaho. Barbara has been a teacher for 11 years. She first taught on the Flathead Indian Reservation in Montana. She currently teaches second grade. Congratulations. And we have a little thing for you. And the winner, the teacher who will be going into space, Krista McAuliffe. Is that you? Krista teaches in Concord High School in Concord, New Hampshire. She teaches high school social studies. She's been teaching for 12 years. She plans to keep a journal of her experiences in space. Well, I'm personally looking forward to reading that journal someday. Congratulations to all of you. Good luck, Krista. And God bless all of you. Thank you very much for coming. And you too get one of these. That's so well done. You want to say something? Or would you rather not? Yeah.
It's not often that a teacher is at a loss for words. I know my students wouldn't think so. I've made 9 wonderful friends over the last 2 weeks. And when that shuttle goes, they might be one body. But there's going to be 10 souls that I'm taking with me. Thank you.
That's great.
The remaining 8 finalists will be staying on the program to help develop the lessons that McAuliffe will be teaching from space. Krista McAuliffe and Barbara Morgan report to Johnson Space Center to start training for their space shuttle mission. The mission they would be training for was assigned STS-51L on Challenger. This naming system for the shuttle flights was necessary for organization, as NASA was planning for a heavily accelerated annual flight rate of 24 per year, or 2 launches per month. A more robust naming convention was called for than had been used on the first 9 missions. STS stands for Space Transportation System and denotes a space shuttle mission. The first number in the sequence is the fiscal year that the launch is supposed to happen. This flight was scheduled to fly in 1986, but since the United States fiscal year runs from October 1st to September 30th, the launch would occur in the fiscal year of 1985. The second number denotes the launch site, 1 for the Kennedy Space Center and 2 for the Vandenberg site. The final letter denotes what sequence in the fiscal year that they will launch. Since this would be the 12th mission in the fiscal year, it would receive the 12th letter, STS-51L. The naming convention change was intended to lower confusion among the separate missions, but it would have mixed results in doing so. For example, delays would cause STS-61C to be launched before 51L. This would be the 24th ever shuttle launch, and the 10th for the Challenger orbiter. The 7 crewmates assigned to this mission are Commander Dick Scobie. This will be his second flight. His first flight was on STS-41C as a pilot, which was also aboard the Challenger orbiter. Pilot Michael Smith, a U.S. Naval test pilot. This will be his first flight to space. Mission Specialist Judith Resnick. This will be her second flight. Her first flight was on STS-41D, the maiden voyage of the Discovery orbiter, where she became the second ever American woman in space. Mission Specialist Ellison Onizuka, an Air Force test pilot. His first flight to space was on STS-51C. This will be his second space shuttle mission. Mission Specialist Ronald McNair previously flew on STS-41B, where he became the second African American to ever visit space. Being a saxophonist, he was planning on recording a solo for A Track in Orbit, the first official music track to be made in space. Payload Specialist Gregory Jarvis, a former Air Force captain and current Hughes aircraft engineer who works on advanced satellites. Originally scheduled for STS-51D, he was replaced by U.S. Senator Jake Garn and reassigned to STS-61C. He would also be replaced on that flight by U.S. Representative Bill Nelson. He was then reassigned to STS-51L. And finally, Krista McAuliffe, a social studies teacher from Concord High School, New Hampshire. Being a member of the public and a school teacher, her presence in this mission would bring significantly more attention than most shuttle flights beforehand, fulfilling the purpose of the Teacher in Space project. Spacecraft can only communicate with the ground if they have a direct line of sight to a station on the ground. Due to this limitation, there are certain points in the shuttle's orbit in which the crew cannot contact mission control. The plan to overcome this obstacle was to deploy geosynchronous satellites that would provide near-continuous coverage between the ground stations and any future shuttle missions. STS-51L's primary mission was to deploy TDRS-B, the Tracking and Data Relay Satellite B. This payload has 2 solid fuel sections that would bring the satellite from shuttle's orbit into geosynchronous orbit 22,000 miles high. The crew on the shuttle could then send their communications to the satellite, which would then beam them back to the ground. This ability would also be incredibly useful for their planned International Space Station. This satellite would work in conjunction with TDRS-A, allowing future space missions to communicate with ground crews throughout most of their orbit. Comet Halley was an object of great importance at this time because it was approaching perihelion, or the closest point to the Sun in its orbit. Its proximity with Earth would also allow measurements to be made about the comet from hardware flown aboard the shuttle. One of those instruments would be the Comet Halley Active Monitoring Program, or CHAMP. This is a camera designed to observe Comet Halley from the shuttle in both visible and ultraviolet light. Another piece of hardware, Spartan 203, is a free-flying module also intended to observe Comet Halley. It would be deployed from the space shuttle, collect data on the comet, and then be retrieved by the shuttle 48 hours later. This mission was deemed moderately complex thanks to the 2 satellite deployments and multiple scientific observations scheduled, as well as the planned retrieval of Spartan 203. McAuliffe's tasks included 2 15-minute lessons, one about the living condition aboard the space shuttle and one about the future permanent space station. She was also scheduled to record demonstrations on microgravity, magnetism, chromatography, effervescence, Newton's laws, and operating machines. This mission was planned to enter an orbit 176 miles high, inclined at 28.5 degrees to the equator, and last a total of 6 days and 34 minutes. Krista McAuliffe and Barbara Morgan began training for this mission early September 1985. McAuliffe would be training for the role of payload specialist, a role intended to allow non-career astronauts to contribute to space missions. This meant that they were to focus mainly on a specific payload that the shuttle would be carrying, rather than going through the full gamut of training to become a career astronaut. As such, most payload specialists only ever flew once. McAuliffe's payload would include items that could easily demonstrate the effects of spaceflight. Her mission was to teach these lessons from orbit, broadcast directly to children in schools in order to bolster public interest and support of these missions.
I didn't realize it'd be so slippery. I should have held on tighter.
Good afternoon. I'd like to introduce to you the commander of STS-51L, Commander Dick Scobie, who will introduce the rest of his crew, and they'll say a few words.
Our fans are over here in the corner. As usual, it's a real pleasure to be at the Cape, to come down here and participate in something that the Cape does better than anybody in the world, and that's launching space vehicles. It's a great pleasure for us to be here. We expect weather like this on Sunday when we launch, and you all do the best to keep it that way if you would. And what I'll do is introduce the next crew member, and we'll just go down the line, let everybody say a little bit as we go. And I'd like to introduce my pilot, Mike Smith, who's one of the best flyers in the world, and he's great to have in the shuttle, and I'm glad to have him aboard as a pilot. So here's Mike.
Thanks, Dick. Let me echo what Dick said about it's good to be down here and to be flying a vehicle that we know a lot of folks down here have worked very hard on. We understand it's ready to go, and we're looking forward to going to fly. I'm one of the 3 people on board who's and it'll be my first time to fly. Krista McAuliffe and Greg Jarvis it'll also be their first time, and we're just all looking forward to getting on orbit and getting the secret handshake. I'd like to introduce now Judy Resnick. She's our center seater, and keeps Dick and I honest on the system problems. Judy.
Well, I too am glad to be here one more time, and I am hoping that the affliction that Steve Hawley had from the 41D mission specialist of the delays hasn't rubbed off on me, and I think the guys behind me are hoping that it hasn't also. Otherwise, they might throw me off the flight. And I will now introduce Ellen Azuka.
Let me say that it's really a pleasure to be back. Looking forward to going to fly this one. I think we got some real interesting payloads. The mission is a great mission. We're looking forward to it, and I think we're ready to go fly. Thanks for being out here today. I forgot the one thing I was supposed to do. Let me introduce Ron McNair, who is going to be doing a lot of work with the Spartan Halley mission and carrying on a lot of the experiments that will be going on in the crew compartment.
Again, I'd like to echo the opinions of my crew members that we look forward to launching from the Cape first of all, and returning here a few days later. I had the privilege of being a part of the crew a couple of years ago that made the first landing here at the Cape, and I intend to be a part of the crew to make the first return landing to the Cape in about a week. At this time, I'd like to introduce you to perhaps the person you came to see, and that's Krista McAuliffe, our payload specialist, teacher in space.
Well, I am so excited to be here. We watched Columbia go over the Houston area this morning, and that was a thrill. I don't think any teacher has ever been more ready to have 2 lessons in my life. I've been preparing these since September, and I just hope everybody tunes in on day 4 now to watch the teacher teaching from space. I'd like to introduce to you someone who's going to be in my 2nd lesson, Greg Jarvis, the payload specialist from Hughes.
It's a great pleasure finally to get this far. I'm very proud to be part of the program that NASA and Hughes have put together, and I'm glad to be representing the Hughes Aircraft Company as their payload specialist. Without any further ado, I'll get off the stage so you can all get going. Thank you very much.
STS-51L was originally scheduled to lift off on January 22, 1986. It would be delayed 1 day and then another due to delays from STS-61C. That day's weather on the transatlantic abort site in Dakar, Senegal required another delay to January 25th. Due to delays from STS-61C, the work requirements for the ground crews could not also meet the requirements to launch 51L, requiring another delay to the 26th. That day, the launch site at the Kennedy Space Center showed unacceptable weather. A cold front was moving in that was projected to appear over the launch site during the launch window. It was decided that they would not be launching that day due to the projected weather. Unfortunately for NASA, when the launch window arrived, the weather was significantly better than had been projected. The cold front came in at 10:30 a.m., an hour after a now wasted launch window. The 27th of January became the first launch attempt with crew ingress to the shuttle. Crowds gather at Kennedy Space Center to watch the launch in person. The crew woke up at 5 a.m. and were strapped into the shuttle by 7:56 a.m.
All 7 members of the 51L flight crew are now in the shuttle, and the orbiter test director, Roberta Wyrick, has verified with the orbiter systems engineers that they are ready to close the crew hatch for flight.
The hatch to the crew cabin was to be latched closed with an external handle, and that handle would be removed.
OVCC, OTC 212.
Go ahead.
How are we doing on closing the hatch?
That's in work right now.
Okay.
We're doing a continuity check.
Upon closing the hatch to the shuttle, a problem had revealed itself.
OTC, OVC.
Go ahead, OVCC.
Okay, on our continuity check, we're only getting one micro switch.
2 micro switches are placed in positions that will tell the crew when the hatch is properly closed, similar to a door or jar signal on a car. One switch was showing that the hatch was properly sealed, but the other one wasn't. It was incredibly important that the hatch be latched closed properly. It was the only thing between the crew and the harsh environment of space.
Let's see if go ahead. Yeah, did you copy that on the hatch? They're only getting 1 micro switch on the continuity check?
That's firm. Could you have them open the hatch back up and close it again?
OVCC, copy that?
Okay, we open that hatch and try it again. We're still getting 1 light. 1 continuity.
This is shuttle launch control at T-minus 50 minutes and counting. The closeout crew in the White Room continuing to work on the hatch to the Challenger. The problem is that only one of the micro switches on the door indicates it's closed once they have it in place.
Yeah, there's some of those latches that we can't see, and if we have a preference, we'd like to have one of the guys that's very familiar with the latches to come inside, close the door, check them to make sure they're all okay, and then send him back out again.
It's requested that a latch technician be inside of the shuttle and closed in to personally observe that the hatch was being properly secured.
It appears that we're going to have one of the closeout crew go into the orbiter and watch the positioning of the various locks on the hatch to determine if they are actually going into the proper position.
Did you have somebody in there and close the hatch? That's affirmative, yes.
Yes, we did. We did it twice. He did not find no anomalies. Yeah, the tech said it looks real good in there.
Okay, Dick, you make sure that the non-passengers leave before we go today.
We'll do that. Thanks.
Okay, did we get both micro switches?
Just one.
This is shuttle launch control at T-minus 30 minutes and counting. They've had a technician in the crew compartment about 3 times now taking a look at the latches on the door. It looks like the door is sealed at the present time. The cabin leak check will verify that.
It is at this point that another problem with the hatch became apparent.
The cabin pressure check has been completed now.
OBC, OTC.
Go ahead, OVCC.
Okay, we got a problem on removing one of the screws on the milk stool. It seems to be stripped.
Okay,
1, 2, 3, 4, 5, test
you are
count out.
working on it, right?
We are working on it.
Okay.
The handle to close the shuttle's hatch was stuck. The screw intended to remove it had stripped out, making it impossible for any tools they tried to get a proper purchase on it.
OTC, VCC.
Go ahead.
Okay, we can't get this one last fastener out of the milk stool. It appears it might have to be drilled out.
OVCC, you're saying you cannot remove it?
That is correct. Yeah, I've been working now for 40 minutes on it.
Okay, do we have the proper tools up there to do that job? OVCC?
That's the negative. I do not have the drill.
Given the risk of working directly next to a space shuttle filled with propellant, they were only allowed to use battery-powered tools near the spacecraft. They would send up a battery-powered drill to drill out the screw and remove it.
The closeout crew had asked for a battery-powered electric drill and the proper drill bits for drilling out the bolt on the access handle. This handle is used only during the time the orbiter is on the ground for moving the door. They also have asked for a hacksaw and have been cautioned by the launch director to be extremely careful during this particular operation. It's not known exactly how long this is going to take. This is a slow operation which must be done very carefully to ensure that there is no damage to the hatch or to the handle.
Unfortunately, because the batteries for the drill had been sitting in the cold outside, as soon as they tried it, they found all the batteries were dead.
Having a problem with the drill, they are in the process of obtaining another drill or another battery pack for that drill.
A waiver would have to be sent up the chain in order to use a wired drill.
Weather forecasters taking very close looks at the weather as we continue to move into this launch window. One of the concerns is the crosswinds at the shuttle landing strip in case of a return to launch site abort. There could be a possible violation of the crosswind constraints, and they are continuing to look at that.
Launch director to Challenger.
LTD, go ahead.
Yeah, Dick and Mike, we're looking at some crosswinds out the runway right now that don't look favorable at all. We're probably going to sit here and wait, hoping for a break, but the best estimate is that the crosswinds are out of spec at the runway and won't improve for the rest of the day. I thought I'd let you know you can be doing some thinking about that.
Okay, Gene, thanks for the heads up. We appreciate it.
Okay.
The wind conditions at the return to launch abort site had picked up beyond acceptable limits.
We have just had a announcement from Launch Director Gene Thomas to the crew and to the launch team that we are going to scrub for today.
Yeah.
OTC, VCC.
Go ahead, VCC.
Okay, we're bringing the crew out now.
Okay. Good.
The winds have been increasing as during the past hour. The weather in the Florida area and the Kennedy Space Center area is going to continue to get much colder. There has been a period of 8 minutes of snow in the Jacksonville area just a short time ago, which is an indication of the way in which the temperatures are coming down as the front moves off and the jet stream brings the extremely cold polar air to the area. The forecast for tomorrow is looking at about 28 degrees Fahrenheit in the launch area at launch time, which would be 9:38. There will be a management meeting at which all of the various aspects of a recycle will be assessed. We'll take a look at the weather over the next 24 hours and make a decision as to whether to try again for Tuesday morning or whether to wait till later in the week.
The launch of STS-51L had already been delayed 6 separate times. With the accelerating flight schedule of eventually 2 shuttle launches per month, unexpected delays like these would become less and less acceptable. Since some of the work procedures from one group could only start when another group finished, delays from one mission would cascade onto other missions and delay those as well. They planned to try again in 24 hours, the next closest launch window. A teleconference would be started to gather any concerns or constraints for this launch from the contractors that make the shuttle's components. There are no recordings of these calls, and so the contents had to be reconstructed from first-hand accounts from the participants. NASA administrators asked if there were any concerns regarding launching the next day at 9:38 a.m. None were brought forward during this initial call. A request is made from this discussion for any other personnel to report any of their concerns that they might have for this new launch date tomorrow. The weather for that day had predicted that the temperatures would drop to 18 degrees Fahrenheit. As Challenger was already rolled out to the launch pad, the entire vehicle would be exposed to below freezing weather conditions for multiple hours overnight. The temperatures predicted for launch that morning weren't much warmer. This would be the coldest launch in space shuttle history. Wanting to make sure there was no objection to launching tomorrow, Boyd C. Brinton, the manager of Morton Thiokol's Space Booster Project, phoned Morton Thiokol engineers Arnold Thompson and Robert Ebeling to discuss the low temperatures. The engineers were asked to evaluate the concerns. Ebeling is especially concerned. He was aware that this launch was planned to happen well outside of the database of temperatures that they had tested previously. Ebeling then meets with Roger Boisjoli, another Thiokol engineer at Utah, and informs him of the plan to launch at low temperatures. Boisjoli was concerned specifically with the O-rings which seal the segments of the boosters together. After each shuttle launch, the boosters are separated from the external tank and deploy parachutes which slow their descent into the ocean below. This allows engineers to recover the spent boosters and then inspect if anything had gone wrong during any part of the burn. One of these previous flights, STS-51B, experienced a complete burn-through on one of the primary O-rings in the nozzle joint. Only the successful sealing of the secondary O-ring saved that flight. Boisjoli was convinced that if this failure had happened in one of the joints between the sections, called the field joints, the secondary O-ring would likely not seal, and the booster would have experienced a catastrophic burn-through. Field joints get their name from the fact that they're joined in the field at Kennedy rather than at the factory at Thiokol. This allows the boosters to be constructed from individual sections which are much easier to cast and that can be shipped by rail to Kennedy Space Center. The bottom of one section, called the tang, would fit inside the top of the previous section, called the clevis. In this way, the sections are stacked on top of each other and then pinned together. 2 O-rings are placed in grooves which seal the segments together and prevent the combustion gases from escaping out of the sides of the booster. Boisjoli was concerned for the fact that both O-rings on the field joints were bore seals, while the nozzle joint had both a bore seal and a face seal. That's why he believed that if 51B's burn-through occurred on the field joint instead, the secondary O-ring would not have held. This was such an issue that he had been specifically assigned to a team that would investigate and put a damper on the erosion. He had felt strongly enough about these issues that he had written a memorandum explaining this and sent it to Thiokol's Vice President of Engineering, Bob Lund. It reads, "The mistakenly accepted position on the joint problem was to fly without fear of failure and to run a series of design evaluations which would ultimately lead to a solution or at least a significant reduction of the erosion problem. This position is now drastically changed as a result of the SRM-16A nozzle joint erosion which eroded a secondary O-ring with the primary O-ring never sealing. If the same scenario should occur in a field joint, and it could, then it is a jump ball as to the success or failure of the joint because the secondary O-ring cannot respond to the clevis opening rate and may not be capable of pressurization. The result would be a catastrophe of the highest order, loss of human life." Boisjoli was well aware of the true magnitude of the risks they would be taking if they were to fly. He wants to delay. Ebeling then calls the director of Thiokol's Solid Rocket Motor Project, Alan J. McDonald. He expresses concern over the joints and the O-rings of the solid rocket booster at low temperatures. McDonald was aware of 51B's near disaster from the O-rings. That wasn't the only launch that showed ominous signs. STS-51C experienced an unusual amount of O-ring erosion on 2 separate field joints. A large amount of soot was found between the primary and secondary O-rings. This was especially concerning for the fact that this was the first time such an amount of soot had been observed between the 2 O-rings. It was also the first time 2 separate field joints had eroded on one flight. That flight was at that point the coldest launch in space shuttle history, at 53 degrees. It seemed apparent to the engineers that the colder temperatures experienced by that flight played a role in its increased O-ring erosion. They were now planning on launching Challenger at just 27. Alan J. McDonald shares Boisjoli's and Ebbeling's view that this flight should be delayed. McDonald then calls Cecil Houston, the Marshall Space Flight Center resident manager, and shares the concerns he and the engineers have around the low temperatures. Cecil would start planning a meeting to begin at 5 p.m. so that a no-launch decision could be made before they started filling the liquid fuel tanks. Cecil would begin contacting all of the relevant parties for their input in the upcoming teleconference. An initial teleconference is held 20 minutes later with the deputy manager of the Space Shuttle Projects Office, Judson Lovingood, and the manager of the Shuttle Projects Office, Stanley Reinhardt, along with other engineers at Thiokol. There is a discussion regarding the effects of low temperatures on the O-rings. The engineers present some concerning data collected from the boosters. STS-51B's nozzle burn-through was discussed. 51C's field joint distress was also discussed. This flight's particularly poor field joint performance was used as justification to support engineering stance that lower temperatures put the flight at risk because they might lose their seal at a low enough temperature. Many of the engineers at Thiokol are sure that the temperatures for the planned launch were far below what the boosters were qualified for. The engineers recommend delaying launch until at least noon, when the temperatures are expected to rise. This initial teleconference ended with the plan that the Thiokol engineers would get their data in order to support their decision to delay launch. They would then present their more refined data during the second teleconference. About 45 minutes later, Lovingood calls Reinhardt and tells him that if Thiokol continues to share concerns around their boosters, they should not launch. They might soon have to send another launch delay up the chain of command. They begin planning on contacting higher-ups at NASA in order to start a launch delay. Then the second teleconference arrived. Managers from both Kennedy Space Center and Marshall Space Flight Center joined the call with concerned Morton Thiokol engineers. Given there wasn't enough time for the engineers to type out most of their concerns, some are handwritten. The data is also presented out of order. Brian Russell begins by presenting a chart outlining some of the observed history of O-ring damage on field joints. Boisjoli presents a chart outlining the concerns from the engineers. Boisjoli knew that at colder temperatures, the material that the O-rings are made of hardens significantly. This would make it harder for the O-rings to seal if the faces they were sealing happened to move away from each other. During the initial development of the field joint, it was intended that the pressure from the motor firing would squeeze close the gap the O-rings are sitting in, helping them seal against the immense pressure inside. However, during testing, the opposite effect was observed. Since the field joint area is 3 times thicker than the walls of the booster, when they're ignited, the immense pressure inside of the booster bows the walls outwards more than the field joint area. This has the effect of rotating the clevis open. This would cause the space that both O-rings are sitting in to open up 60 thousandths of an inch. This event was given the name joint rotation by the engineers and was considered an acceptable risk even though the design was not working as intended. All shuttle flights up until this point were flown in this configuration. Arnold Thompson then presents his charts and attempts to convince the managers that temperature is indeed a factor in the O-ring's ability to seal. He presents data collected from tests where an O-ring would be cooled to different temperatures and then squeezed by plates. The plates would be moved back to their original position, and the time it took the O-ring to recover to its original shape was measured. It showed that at 100 degrees, the O-ring never lost contact with the plates moving away from each other, while at 50 degrees, the O-rings took 10 minutes to regain contact with the plate. He presents another chart which emphasizes the fact that the O-rings harden when they get colder. Boisjoli's main concerns were in regard to the combination of the cold O-rings and joint rotation. During a usual ignition and launch, the O-rings would be pushed into their sealing position by the pressure buildup inside of the booster before the joint rotates. This causes the O-rings to be in the proper position to seal even during joint rotation. However, if those O-rings were cold, it would cause the material to not be able to rebound during joint rotation and fill that gap created. The seals in that configuration would have no chance of holding back the immense pressure inside of the boosters. Since both the primary and the secondary O-rings would suffer these effects at the same time, a gap would be created in which hot combustion gases and products would blow by, destroying the seal. If this scenario were to happen, it would be expected that the vehicle would blow up on the launch pad, killing the crew and destroying a multi-billion-dollar vehicle and launch facility in the process. The evidence the engineers have that they're losing their seals at a low temperature are in their charts comparing the launch temperature and O-ring anomalies. Many of the flights with field joint anomalies were launched at colder temperatures, STS-61A being a notable exception. Malloy, noticing that 61A was one of the warmest launches to date at 75 degrees, then interjects, "How can you conclude that temperature has anything to do with blow-by?" Fragility responds that the erosion on the O-rings used on 51C was significant and covered a much larger area than the soot observed on 61A. 61A had shown no primary O-ring erosion and was only affected on a 30 to 40 degree section on that O-ring. Fragility continues, "I feel strongly that the observed difference between these two flights is most probably due only to temperature. That STS-51C had O-ring temperatures of 53 degrees and STS-61A had O-ring temperatures of 75 degrees. Malloy and Hardy were not convinced. Fragility's claims were contrasted by the fact that multiple shuttle flights had been launched between 53 and 75 degrees, most of which showed no field joint erosion. Malloy thought the temperature was not a concern and that the data presented was inconclusive with the engineer's recommendation to delay launch. This chart showed no blow-by at 30 degrees. Someone asked why they would still think temperature would be a concern given that. Thompson responds by saying the tests used to acquire this data don't adequately simulate the conditions of SRB ignition in real life, as they don't take into effect the joint rotation from ignition. Bob Lund finally conclude that they believe the shuttle should not launch unless temperatures are higher than 53 degrees. He submits the engineer's conclusions and then this written recommendation to the managers at NASA. Lund adds that they might want to delay launch until later that afternoon when temperatures are expected to rise. Malloy asked if this was the end of the presentation. Lund says yes. Malloy asks Kilminster for his input. He replied, since the engineering recommendation is to delay launch, he could not recommend launch. The managers at NASA were, to put it lightly, less than thrilled by this decision. Malloy allegedly stated, "I have a contrary opinion." He spoke for about 5 minutes. He believed the data presented was not conclusive and did not support Thiokol's recommendation to delay launch. Temperature could not be correlated with the performance of those O-rings on prior flights. This recommendation was especially confusing for the fact that they had accepted temperatures lower than 53 degrees on previous flights, they just hadn't launched those flights because they had been delayed for other reasons. The temperature that they had just agreed to launch the day before was 37 degrees. They cancelled that launch attempt because of winds at the return to launch abort site, not temperature. Thiokol had raised no concerns about temperature that day. Their own data showed similar blow-by effects on a room temperature launch. Even if the primary eroder fails, they have a secondary O-ring in a much better place to seal. Even in the worst case situation, the secondary O-ring will seat in less than 170 milliseconds, which is less time than it takes for significant joint rotation, ensuring a proper seal. The same rationale that was being used to delay launch under 53 degrees could also be used to justify a recommendation to delay launch under 75 degrees, which would be an obviously ridiculous request. To Malloy, Thiokol was coming out with a surprising recommendation out of the blue which would have serious effects on future mission schedules on the eve of a launch when they had never even so much as requested a delay before. And they were doing this with very obviously inconclusive and incomplete data. This temperature recommendation was also surprising for the fact that they were planning to start launches from Vandenberg, many of which were to happen under the 53-degree recommendation. Reinhardt states that he was told that the boosters can withstand temperatures between 40 and 90 degrees Fahrenheit, so a recommendation of launching no lower than 53 degrees didn't make sense. It was inconsistent with what they had been told before about their boosters. Thiokol's own chart showed the O-ring sealed as expected at 30 degrees. Thiokol had also shown that they were perfectly fine with launching below 53 degrees as that's what the temperature was during the first launch attempt. Malloy chimes in with, "My god, Thiokol, when do you want me to launch? Next April? The eve of a launch is a hell of a time to be generating new launch criteria." Reinhardt asks Hardy for his input. George B. Hardy then said to the concerned engineers at Thiokol, "I am appalled. I am appalled by your recommendation." He was previously told the boosters could withstand temperatures lower than 53 degrees, but he wouldn't launch against Thiokol's recommendation. Hardy states that their concerns only address the primary O-ring and that there is a secondary O-ring in a better position to seal if the first one fails. After the stacking of the solid rocket booster sections, a leak check is performed by blowing compressed air through a port in between the primary and secondary O-ring. The space in between the O-rings would be held at 200 psi. If the pressure didn't drop past a certain amount, they could then conclude that the O-rings were sealing properly. One significant difference that the leak check has with actual ignition is the fact that the pressure for the leak check is provided through a port between the two O-rings before flight. This has the effect of pushing the primary and secondary O-rings away from each other. During the leak check, the primary O-ring would be shoved into an upwards position by this test and the secondary into a lower position. Since the O-rings could not be accessed after the segments were stacked, they would be rolled to the launch pad in this condition. For each flight, the primary O-rings would start on the launch pad shoved into the wrong side of its O-ring groove. This was a known event. During launch, the primary O-ring would be shoved downwards into its correct position by the pressure inside of the solid rocket booster. This would seat the O-rings and allow them to seal the segments for the duration of the flight. Hardy was making the point that since the secondary O-ring would be shoved backwards by the leak check, it would be in a much better position to seal compared to the primary O-ring during joint rotation. Malloy then asks for Kilminster's input, who then reiterates that since the engineers recommend delaying launch, that he can also not recommend launch. The managers at NASA challenge the conclusions and the recommendation to delay launch. They claim the data is inconclusive and thus shouldn't be used to create an entirely new launch constraint a day before liftoff. Malloy mentions that blow-by had been noticed on warmer launches. Jerry Mason turned to Joe Kilminster and said, "Joe, ask them for a 5-minute caucus offline." Kilminster then asked the call for a 5-minute break. McDonald makes his first statement of the teleconference, that they should reassess the point Hardy made with the primary O-ring being out of position but the secondary being in the correct position. He did not intend it to be, but this was interpreted by everyone as an argument supporting launch. This statement was baffling to the engineers who were trying to make the argument that it was not safe to launch. The 5 minutes is granted to Thiokol to assess their data. The caucus begins by Jerry Mason stating that a management decision was necessary. Boisjoli, Thompson, Russell, and Ebeling are adamant that they should delay launch. Mason and Wiggins aren't convinced that temperature is a concern. Lund is on the fence. The engineers go over their data again, emphasizing the need to delay. Boisjoli was asked whether he had any data that supported his conclusion that O-ring erosion and temperature were correlated. He said he had been trying to get more data from their Instron machine since October, but problems with the machine had caused its readings to be unusable. To this, Mason gave Boisjoli a stern look. He was not pleased with the reasoning being used. The engineers repeatedly go over the data, emphasizing the effect of temperature. Even if they went with the more risky 40-degree temperature cutoff, they would still be well below that. Mason asked them to remember McDonald's comment about the secondary O-ring being in the correct position to seal. Boisjoli and Thompson don't know what the secondary O-ring will do, so they don't want to rely on it. Jerry Mason makes the direct statement, "Am I the only one that wants to fly?" The engineers agree that temperature is a significant enough concern for the boosters to delay launch. Management does not share the same concerns. They believe the data does not show the temperature is a concern. An unexpected temperature constraint like this would have serious implications, grounding the entire fleet for large sections of their launch windows, particularly for the planned Vandenberg launch site. Management wanted solid data that showed temperature was a concern. As the engineers were unable to do that, managers believed the conclusions they were drawing weren't supported or realistic. Management believed they were being overly cautious, and an accelerating shuttle launch schedule wasn't compatible with halting the entire fleet for every unsupported concern. Boisjoli and Thompson repeatedly go over the same data points. Given the very limited data they have, it isn't very convincing. Mason, noticing there was no new data that could be brought up, then said, "Well, it's time to make a management decision. We're just spinning our wheels." Arnold Thompson walked up in front of the managers with a notepad and attempted to draw out the problems they were concerned with. Halfway through his explanation, he realized he wasn't getting through to them and stopped. The data, including their own charts, does not conclusively show that temperature will cause a seal to fail. Mason stated that he could not disagree with Malloy. The data was inconclusive with the engineer's beliefs. There is a secondary O-ring that is in a better position to seal. He recommends launch. A management decision would have to be made. This one would exclude the engineers and only poll the managers. Mason asked Cal Wiggins if he supported launch. He agreed. Kilminster supported launch as well. Mason then asked Lund whether he supports launch. Lund was reluctant. All of the managers support launch. All of the engineers want to delay. He looked to the engineers for more data. They didn't have anything new to offer. That was all the information they had to work from. Being the last manager to make the call, the weight of the entire shuttle program was now on Lund's shoulders. The 5-minute break had turned into 30. Mason asked Lund to take off his engineering hat and put on his management hat. He concedes. 51L will launch tomorrow. As Thiokol were on mute during their caucus, McDonald would not be aware of the conversation happening there. At Kennedy Space Center, he's still arguing the concerns he shares with the engineers. "I don't believe that every component and element of the SRM is qualified to 40 degrees. My interpretation of the specification is that 40 to 90 degrees is the operating temperature range and includes all components of the SRM. Malloy retorts, "The 40-degree requirement applies to propellant mean bulk temperature only, and STS-51L at the time of launch will be at 55 degrees. That means other components can be below 40 degrees as long as the PMBT never drops below this value. That's ridiculous, Larry, because the propellant is such a massive insulator that it never changes the PMBT in a few hours, even with tremendous external temperature changes. I'm sure the specification didn't mean that. It could be 100 degrees below zero outside for several hours and it wouldn't change the PMBT by more than a few degrees. NASA should consider delaying the launch until late afternoon. Malloy responds, "We've considered this and rejected it because of problems with weather and maybe visibility at one of the transatlantic abort landing sites." The teleconference is resumed. Thiokol came back on the line and Joe Kilminster stated that they had internally reassessed the situation. He reads off the rationale for a recommendation to launch. "We've reassessed the data and concluded that even though temperatures are a concern, the temperature effects are inconclusive. Therefore, Morton Thiokol recommend launch." Thiokol had reversed their initial position of not launching. Reinhardt asked if there were any disagreements with the new Thiokol recommendation. None were brought up. Hardy requests signing and faxing a written recommendation of launch from Thiokol to both Kennedy and Marshall Space Centers. This struck McDonald as particularly odd. He writes about this decision in his book about this event, Truth Lies in O-Rings. No one from NASA had asked any questions about the validity of the data used to change the recommendation from don't launch to launch, whereas they had challenged nearly all the data Thiokol had presented before the caucus. It was clear that NASA had finally gotten the answer it wanted. NASA's Lawrence Malloy had looked me directly in the eye from across the table at Kennedy Space Center when the request was made to put the launch recommendation and rationale in writing and sign it. I told Malloy that I would not sign that recommendation and that it would have to come from the plant in Utah. It appeared to me that the need for the signature on the launch recommendation was for CYA or cover your ass purposes only. This indicated to me that even though NASA officials got the verbal recommendation they wanted, they weren't comfortable with it either, or they wouldn't have requested the signature. A request to provide a signed recommendation to launch after an L1 flight readiness review had never happened before in the history of the shuttle program. I didn't feel good about any recommendation that could lead to a launch at a temperature below 53 degrees just because our engineers felt forced to concede after a 3-hour discussion that their data was inconclusive. McDonald, still holding the view that they should not launch under the projected conditions, states to the conference room that if anything happens to this launch, I wouldn't want to be the person that has to stand in front of a board of inquiry to explain why we launched outside of the qualification of the solid rocket motor. To which he was told, "These really aren't your problems, Al. You really shouldn't concern yourself with them." The below freezing temperatures would have its own effects outside of the vehicle as well. As water pipes line most of the launch tower, and there wasn't enough time to drain them before launch, the decision was made that water would instead be allowed to flow through them to avoid freezing and bursting the pipes. This flowing water would then mist back onto the tower, freezing onto it and forming large icicles throughout most of the structure. Ice teams determined that ice wouldn't hit anything and so it wouldn't be a problem. Driving his daughter to a live viewing of the Challenger launch at the Thiokol facility, Ebeling made his discontent with the decision to launch clear. He said, "According to our engineering people, 51L is going to blow up on the pad. The Challenger is going to blow up. Everyone's going to die." He was so frustrated with the decision he was punching the dashboard. The public would fill the viewing stands to watch the long-delayed launch. As planned, classrooms around the nation would roll the television into the room so the class could watch the launch of the teacher in space. An estimated 2.5 million students would be watching the live broadcast.
We see the 51L crew enjoying breakfast. Mission Specialist Ellison Onizuka sitting beside teacher in space participant Krista McAuliffe. They are posing for their traditional shot during their breakfast. And then we have Commander Dick Scobie sitting beside pilot Mike Smith in front of the traditional cake featuring Halley's Comet and an apple for the teacher. Judy Resnick on the left, mission specialist, along with Ron McNair and payload specialist Greg Jarvis, all members of the 51L crew. And they're going to give it another shot today. including teacher in space participant and the first private citizen to fly in space, Krista McAuliffe. And this is the work crew here that has been very active in preparing the 51L mission at the Operations and Checkout Building. The payloads, which include a TDRS satellite, the Spartan Halley experiment, and here comes the flight crew now. Commander Dick Scobie, followed by Mission Specialist Judy Resnick, Ron McNair, and pilot Mike Smith, followed by Krista McAuliffe, teacher in space, and Ellison Onizuka, and payload specialist Greg Jarvis. Big smiles today. Confidently getting into the van. They're going to go out to that pad and attempt a second try. Second try at launch today.
And we're at T-minus 9 minutes and counting. The ground launch sequencer program has been initiated.
Your APU bus recorded? Sure, yes, will do. And LPS place all finder plotters online. LPS coming.
This is the walkway used by the astronauts to climb in the vehicle, and that arm can be put back in place within about 15 to 20 seconds if an emergency should arise. T-minus 2 minutes and counting. The liquid hydrogen replenish has been terminated, and liquid hydrogen pressurization to flight level is underway. The vehicle is now isolated from all ground propellant and fluid loading equipment. T-minus 30 seconds, and we've had a go for auto sequence start. The SRB hydraulic power units have started. T-minus 21 seconds, and the solid rocket booster engine gimbal now underway. T-minus 15 seconds. T-minus 10, 9, 8, 7, 6. We have main engine start. 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Challenger.
Good roll, flight. Brad, good roll.
Good roll program confirmed. Challenger now heading downrange.
Throttle down at 94. 94.
Engines beginning throttling down now at 94%. Normal throttles for most of the flight, 104%. We'll throttle down to 65% shortly. Engines at 65%. 3 engines running normally. 3 good fuel cells. 3 good APUs.
Thank you.
Velocity 2,257 feet per second. Altitude 4.3 nautical miles. Downrange distance 3 nautical miles.
Throttle up, 3104. Depcom, go at throttle up.
Engines throttling up. 3 engines now at 104%.
Challenger, go at throttle up. Challenger, go at throttle up.
Holy shit! Oh, everybody in!
Fido, trajectory.
Bring it down!
Go ahead. Trajectory, Fido. Flight Fido, sensors got this thing sorted. Here we go. Flight J2, we've had negative contact, lost assembly. Okay, all operators, watch the data carefully.
No.
Flight Fido's going to get stuff back. You don't have to cards for the boat modes. Procedures, any help? Negative, flight, no doubt.
Flight controllers here looking very carefully at the situation. Obviously a major malfunction. We have no downlink.
Flight Fido, go ahead. RSO reports vehicle exploded. Copy. Fido, can we get any reports from recovery forces? Stand by. JC, all operators, contingency procedures in effect.
We have a report from the flight dynamics officer that the vehicle has exploded. Flight director confirms that. We are looking at
checking with the recovery forces to see what can be done at this point.
Vital flight, go ahead. LSO and recovery forces, any contacts?
Contingency procedures are in effect.
We're working with the flight. Okay.
We will report more as we have information available. Again, to repeat, we have a report relayed through the flight dynamics officer that the vehicle has exploded. We are now looking at all the contingency operations and awaiting word from any recovery forces in the downrange field.
Vital flight, go ahead. Do the RSOs have an impact point? Stand by. Flight Vital, go ahead. Vacuum IP is 28.64 north, 80.28 west. How does that stack with the solid recovery forces? We're still talking to them. Okay. Okay, everybody, stay off the telephones. Make sure you maintain all your data. Start pulling it together. Booster flight. Flight booster. Did you see anything? Nothing, sir. I looked at all the turbine temps are perfect, right on the prediction. All the red lines are in good shape. Army. We look good, fine. Ecom. Ecom flight. Flight Ecom, we look normal. DPS. All our data's normal. Prop. Everything looked good, flight. GMC. Flight, the roll maneuver looked fine, but we saw that we were on our way decreasing roll rate as we lost data. Copy. Flight, Vital flight. Go ahead, sir. Are the LSOs on the loop? We can get them. Get them up on this loop, please. Over up. Yes, sir. It's the LSO. Okay, are there any forces headed out that way? Yes, sir. DOD LSO reports that all SOC forces have been scrambled and they are on their way. Okay, we have an ETA? Negative, sir.
"73 seconds after liftoff, Challenger explodes. Debris from the vehicle was recorded streaming from the explosion, falling into the ocean below. Recovery ships are scrambled to collect debris and find the crew cabin. The accident happened at 46,000 feet, or 14 kilometers above the ocean. There are no abort modes for this type of accident. The vehicle was simply not designed to handle this type of event. The crew is pronounced dead." Originally planning for a State of the Union speech that day, Reagan cancels those plans to instead address the nation about the disaster they had all just witnessed.
Ladies and gentlemen, I'd planned to speak to you tonight to report on the State of the Union. But the events of earlier today have led me to change those plans. Today is a day for mourning and remembering. Nancy and I are pained to the core by the tragedy of the Shuttle Challenger. We know we share this pain with all of the people of our country. This is truly a national loss. 19 years ago, almost to the day, we lost 3 astronauts in a terrible accident on the ground. But we've never lost an astronaut in flight. We've never had a tragedy like this. And perhaps we've forgotten the courage it took for the crew of the shuttle. But they, the Challenger 7, were aware of the dangers, but overcame them and did their jobs brilliantly. We mourn 7 heroes: Michael Smith, Dick Scobie, Judith Resnick, Ronald McNair, Ellison Onizuka, Gregory Jarvis, and Krista McAuliffe. We mourn their loss as a nation together. To the families of the 7, we cannot bear, as you do, the full impact of this tragedy. But we feel the loss, and we're thinking about you so very much. Your loved ones were daring and brave, and they had that special grace, that special spirit that says, "Give me a challenge, and I'll meet it with joy." They had a hunger to explore the universe and discover its truths. They wished to serve, and they did. They served all of us. We've grown used to wonders in this century. It's hard to dazzle us. But for 25 years, the United States space program has been doing just that. We've grown used to the idea of space, and perhaps we forget that we've only just begun. We're still pioneers. They, the members of the Challenger crew, were pioneers. And I want to say something to the school children of America who were watching the live coverage of the shuttle's takeoff. I know it's hard to understand, but sometimes painful things like this happen. It's all part of the process of exploration and discovery. It's all part of taking a chance and expanding man's horizons. The future doesn't belong to the faint-hearted. It belongs to the brave. The Challenger crew was pulling us into the future, and we'll continue to follow them. I've always had great faith in and respect for our space program, and what happened today does nothing to diminish it. We don't hide our space program. We don't keep secrets and cover things up. We do it all up front and in public. That's the way freedom is, and we wouldn't change it for a minute. We'll continue our quest in space. There will be more shuttle flights and more shuttle crews, and yes, more volunteers, more civilians, more teachers in space. Nothing ends here. Our hopes and our journeys continue. I want to add that I wish I could talk to every man and woman who works for NASA or who worked on this mission and tell them, your dedication and professionalism have moved and impressed us for decades, and we know of your anguish. We share it. There's a coincidence today. On this day, 390 years ago, the great explorer Sir Francis Drake died aboard ship off the coast of Panama. In his lifetime, the great frontiers were the oceans, and a historian later said he lived by the sea, died on it, and was buried in it. Well, today, we can say of the Challenger crew, their dedication was, like Drake's, complete. The crew of the Space Shuttle Challenger honored us for the manner in which they lived their lives. We will never forget them, nor the last time we saw them, this morning, as they prepared for their journey and waved goodbye and slipped the surly bonds of earth to touch the face of God. Thank you.
The media took the conversation from here.
For those of you who may have just joined us, tragedy in the skies over Florida this morning at 11:39 a.m., 1 minute after liftoff. Challenger exploded in a ball of fire.
My God, a major tragedy. The shuttle has exploded. The Challenger has exploded.
It appears to have killed all 7 crew members, including the first private citizen in space, school teacher Krista McAuliffe.
This is indeed a tragedy. There appears to have been an explosion.
With its 3 engines at the base, takes its fuel from here. Now, the whole thing was still together. About a minute
we have no
seconds.
downlink is the word from Mission Control. Something has gone gravely wrong, and the shuttle itself
it's disappeared.
Has not been heard from. Disappeared in a cloud of smoke.
Is that the president, like all Americans, watched this on television, and he felt very keenly the emotion that must be felt by the families of those down there and that had to watch this event in person, and very keenly what the American people must
thrust.
feel.
And the last words that we heard from the space shuttle said, Roger, go to throttle up. That's go to throttle up. That is to go to maximum thrust. And within a second or
shuttle
two,
or whatever. But at this point, I think it's way too early to speculate.
And the cold weather. This is something new for NASA, too, isn't it?
Yes, but I don't think the cold weather really had anything to do with this type of thing.
Will we ever know what happened? Is there the equivalent
when it
of a
appears
black
the
box?
explosion took place. Now, I must emphasize again, Dan, these are only theories. We have not heard anything from NASA. These are the theories of people who are looking at the tapes here, and they are also looking in slow motion trying to make some determination.
Reviewing footage from the event, a plume of fire can be seen escaping from the right-hand solid rocket motor just before the explosion. For the first time, the public was given someone to blame for the deaths of the crew. The contractor that built the solid rocket motors, Morton Thiokol. The media would begin contacting all of the engineers and managers who worked on the boosters. President Reagan signs Executive Order 12546 creating the Rogers Commission in order to investigate the incident.
It's been almost a week since our nation and families stood together as we watched Challenger slip beyond our grasp, the memories of that moment will be with us always, as will the memories of those brave Americans who were aboard. The death of the astronauts and the destruction of the Space Shuttle Challenger will forever be a reminder of the risks involved with space exploration. And we will always remember the Challenger 7. As we move away from that terrible day, we must devote our energies to finding out how it happened and how it can be prevented from happening again. It's time now to assemble a group of distinguished Americans to take a hard look at the accident, to make a calm and deliberate assessment of the facts and ways to avoid repetition. So I am today announcing the formation of a presidential commission on the Space Shuttle Challenger's accident. The commission will review the circumstances surrounding the accident, determine the probable cause or causes, and develop recommendations for corrective action. And this commission will report back to me within 120 days. William P. Rogers, former Secretary of State and former Attorney General, will serve as chairman of the commission, and Neil Armstrong, former astronaut, will serve as its vice chairman. In addition, today we are announcing 10 of its members drawn from distinguished leaders of the government, scientific, technical, and management communities. The crew of the Challenger took the risks and paid the ultimate price because they believed in the space program. They were excited by the mystery of what is beyond the Earth and to the limitless possibilities of space exploration. They knew of the dangers they faced. Yet despite those dangers, they chose to go forward, not reluctantly, but eagerly and with a thumbs up. And we owe it to them to conduct this investigation so that future space travelers can approach the conquest of space with confidence, and America can go forward with enthusiasm and optimism which has sparked and marked all of our great undertakings.
Members from the Rogers Commission included members from both academic and spaceflight backgrounds. The hearings would be public. They begin on February 6th. These hearings included administrators, managers, and engineers from both NASA and Morton Thiokol who would be asked questions about the shuttle and eventually their decision to launch. They started with a wide view of how the entire vehicle works and its individual components. They went over general information about the orbiter, the external tank, and the solid rocket boosters. They do not mention the field joints. Eventually, this causes one of the commission members, Dr. Walker, to ask, "Are you planning to discuss the way in which these sections are joined?" I had not planned to go into any detail on that. There's a field joint approximately right here, and the field joint is what we call the joint between the two segments that are cast individually, separately, and that joint is made at Kennedy Space Center. Are these Viton O-rings? Yes, that's correct. What we can do is, I had not planned to focus, the instructions I had for this was just to give you an overview. I had not planned to focus on any particular area, and that's why I'm not prepared to do that. Well, we can come back to that. We appreciate that we didn't give you much notice of the meeting, and so proceed. We will be able to get that information. Not planning to talk about the field joints was a mildly concerning development for the fact that flames could be clearly seen coming from the field joint area just before the explosion. Given these were the start of the hearings and they were expected to go into more detail later, this point was not brought up. Lovingood himself was present during the entire decision-making process regarding the O-rings, including the caucus at Thiokol, and would have been aware of the engineers' concerns over their performance for that launch. Lovingood did not use this opportunity to make the commission aware of the engineers' concerns. How about the operating limits on this motor? It says in the manual that it ought to operate between about 40 and 90 degrees Fahrenheit. Of course, it was a lot colder than that. The requirement is on propellant mean bulk temperature, and in fact I had a chart on that is one of our requirements, and it was predicted that the mean bulk temperature would be 55 degrees at launch, and it's been reported to me that that's what it was, about that value. So we do have a requirement to be between 40 and 90, and we were within that range. Now that's all I had on the booster. I want to comment that there were questions earlier. I think the gentleman who was asking the question has left. There was a question earlier about, I think he phrased it, a concern by Thiokol on low temperatures. We did have a meeting with Thiokol. We had a telecon with people in Huntsville, people at the Wasatch Division, and people at Kennedy Space Center. And the discussion centered around the integrity of the O-rings under lower temperature. We had the project managers from both Marshall and Thiokol in the discussion. We had the chief engineers from both places in the discussion. And Thiokol recommended to proceed on the launch, and so they did recommend the launch. We had a meeting where there was some concern about the cold temperatures. When was that meeting? That was the 27th. They started around 4:45 Central Time. Is there anything else on the booster? I guess not. Going on to the external tank project. During these hearings, the managers were asked questions regarding concerns they had been aware of that day. Lovingood stated simply that Thiokol had some concerns, but they had signed off on the flight. Given that these hearings were public, many other NASA engineers and managers were watching. This statement struck a budget analyst by the name of Richard Cook as particularly odd. Witnessing NASA's reluctance to share the engineers' concerns with their boosters, he decided to take action. He had been aware of the push to try to get more funding to properly address the O-ring erosion concerns. It was his job to watch the budgeting for each component, and it was his opinion along with the engineers that the problems with the O-rings were not being properly funded or addressed. Cook had shared the concerns the engineers had with their O-rings before the launch of 51L. Having felt that not enough action was being done at the time to address those concerns, he wrote and submitted a memo to NASA outlining the need for more funding to address the O-ring erosion. He had held on to a copy of his memo that he was now handing over to the New York Times to publish. He was going public with his concerns in hopes that this information would end up in the hands of the Rogers Commission, forcing NASA to answer for why those concerns were never addressed. On February 9, 1986, the New York Times published Richard Cook's memo which points to the O-rings as a direct concern. This report eventually made its way to the Rogers Commission. The paper states, "The space agency was warned last year that seals on the space shuttle's solid fuel booster rockets might break and cause a catastrophic accident, according to documents from the agency's files. The documents show that the engineers at the headquarters of the National Aeronautics and Space Administration and its Marshall Space Flight Center in Huntsville, Alabama were concerned that leaks might occur where segments of the booster rockets are mated. Such leaks would allow hot gases and flames to escape through the side of the rocket instead of through the nozzle that channels the gases out of the rear, possibly causing severe damage to the shuttle or an explosion, according to space experts. A stark warning. The fact that the Commission was hearing, for the first time, that the O-rings could be the primary cause of the Challenger accident was incredibly surprising to them for the fact that they were not learning this from NASA, but a leaked report in the press. The Commission was not happy with this fact, and so a closed emergency meeting was called to start the next day to brief the Commission on those memos and concerns. This meeting was closed off from the public in hopes that NASA would become more transparent. Alan MacDonald would be in this closed meeting, but since he wasn't expected to present anything, he would be seated in the viewing stands in the back. Rogers gives NASA a chance to explain themselves in this closed meeting why this memo was supplied to the media but not them, and what they did to address those concerns. An administrator from NASA, Michael Weeks, attempts to explain the situation to the Commission. I put this briefing together to address the New York Times article, and then I will go into this chronology of things that have happened on the O-ring problem since we first ran into it. The Cook Memorandum was written on the 23rd of July, and it was prepared by the financial analysts over in the financial department, and the person is a financial type person and not too knowledgeable of the whole program situation. Let's focus up for a moment on the Cook Memorandum. As I understand it, you're saying that he was just hired and was in a department where he really didn't have much knowledge of what was going on? Mr. Weeks, could you tell us whether there are any errors of fact in this memo, and if so, would you point them out? We can get Mr. Cook here if you would like, Mr. Chairman. Yes, we would like that, but just go ahead. We will get an answer to that. Just so we understand, this says, discussion with program engineers show that these are potentially major problems affecting both flight safety and progress cost. My question is what he set forth in there accurate? And didn't he talk to the engineers and deduce this information? Isn't this information he got from the engineers? I think his statement in there where he says that it might be catastrophic, I think is overstated. Well, that may be. I think the best thing for us to do, Mr. Chairman, is to think about getting Mr. Cook here, and then we can ask Mr. Cook to sit down and try to answer your questions on this thing. Yes, but we want to ask questions as we go along. We would also like your opinion on whether this is accurate or not. This is a case where you're saying, in effect, that you didn't have much confidence in this fellow because he was in the wrong department and had been there just a short time, and so we're asking, is the material that he reported on accurate? I think it's substantially accurate. Let me go back just one moment to the Cook Memorandum. You'll notice at the end of that, he ties safety to budgetary considerations. He said, I would think that any NASA budget submitted this year for fiscal year 1987 and beyond should certainly be based on a reliable judgment as to the cause of the SRB seal problem and a corresponding decision as to budgetary action needed to provide for its solution. Do you know whether any such action was taken or consideration was given to this memorandum on this point? I can state authoritatively that no action was taken. I think this is true of Mr. Moore as well, because I didn't see this memorandum until yesterday. Do you know whether anybody else took it seriously then? We certainly were alert. As you will see as we go through this whole chronology, you'll see that we were alert to a problem, but we had not identified a precise amount of money that we thought we would be required to fix it. Sir, may I comment on the Cook Memorandum? Mr. Cook is in our budget office at NASA headquarters. I understood that. Now, he wrote this internally to one of the people in the budget office. To my knowledge, no one in my office, at least in the technical program area here, saw this memo from Mr. Cook. Let me say that I fully understand that, but we want to be sure that we face the facts. The fact is you have a memorandum, and Cook says certain things that he thinks should be done. All I want to do is find out what was done. If it wasn't done, tell us why and we will understand and the record will be clear. That's all. We will have to bring in Mr. Cook, I think, to make sure of that, or we can provide you a written statement. No, we would like to have them. There are documents that are test results that are even now in progress of some tests that have been done previously to understand the resiliency of O-rings at various temperatures. I believe also, Larry, that there was a discussion in close proximity to the launch between you and other people at Thiokol. Yes, when we stood down on the 27th, it was known that the temperatures were predicted to be below freezing during the night and into the morning on the 28th. As a matter of routine, those of us working the launch asked our technical people and our contractors what concerns we might have for low temperatures, and that was immediately after the stand down. The only concerns that were presented to me were for the recovery battery temperatures. That was analyzed and it was concluded that we did not have a problem at the recovery batteries, that we would be above the red line limit on the recovery batteries at launch time, given the temperatures. At about 7 on the evening of the 27th, I received a phone call from Stan Reinhardt, who is my immediate supervisory, and he had been informed by our resident manager that Thiokol had looked at the conditions for the solid rocket motors and wanted to discuss the situation as they saw it for launch. And Stan Reinhardt and I went to our resident office and we had a telecon. That telecon involved Reinhardt, myself, and a Thiokol representative, and Al McDonald at Kennedy Space Center, a number of people at Marshall Space Center, including Dr. Lovingood, and probably 8 or 9 other people, and probably a dozen or so people at Thiokol. Thiokol presented to us the fact that the lowest temperature that we had flown in an O-ring or a case joint was 53 degrees, and they wanted to point out that we would be outside of that experience base. Who did that for Thiokol? That was the director of engineering for Thiokol, a gentleman named Bob Lund. After hearing the discussion, we all concluded that there was no problem with the predicted temperatures for the SRM, and I received a document from the solid rocket motor project manager at Thiokol to that effect, that there was no adverse consequence expected due to the temperatures on the night of the 27th. I guess maybe what I'm asking is, we read in the New York Times about NASA internal memos where people within NASA were suggesting problems with erosion before, and I guess I'm wondering whether similar memos exist relating to problems with launching with the O-rings at low temperatures. I'm not aware of any such documents at Marshall. Can we then make it clear that we have requested such documents, and if there are any, that you will provide them? This testimony from Malloy was surprising to Alan McDonald because both of them had been at Kennedy Space Center during the teleconferences, and both of them would have been aware that Thiokol submitted a written recommendation not to launch under 53 degrees. Malloy was attempting to downplay the importance of the teleconference by suggesting that Thiokol was simply bringing up the fact that they would be launching outside of their experience base, rather than the fact that they had fully recommended against launch specifically due to the temperatures. Through the testimony NASA officials were giving, it became clear to McDonald that NASA was attempting to cover up the fact that Thiokol had originally recommended not to launch. They were presenting the story that Thiokol was only somewhat concerned with the temperatures, but still gave the go-ahead to launch. Although these facts were true on the surface, the story greatly minimized the serious concerns that the engineers at Thiokol had about the launch. They never mentioned that they had first recommended not to launch, and also left out the fact that those engineers had never changed their recommendation. McDonald had decided that he had had enough. Raising his hand, he was going to make the commission aware that Thiokol had originally recommended against launch. I wanted to say a point about the meeting. That meeting was called by Thiokol. The meeting was set up to send material on the facts so that people could review data and concerns and the basis for that concern. That data was transmitted to Kennedy and also to Marshall from our office at Thiokol. The recommendation at that time was not to launch below 53 degrees Fahrenheit because that was our lowest acceptable experience base and did demonstrate some blow-by from a year ago. And also we had some data that indicated the poor resiliency of response of the Viton seal to low temperatures. You said not to launch below 53, and what was the actual temperature? The actual temperature predicted at that time, based on Thiokol's calculations, was 29 degrees. When the concern of the predicted cold temperatures at the Cape were transmitted to our plant, our engineers were asked to examine that and see if there was any concern about launching the SRM or any concern with any component. The people who were working the O-ring seal problem were concerned. They called me at the Cape and said we looked at these predicted temperatures. It looked like the O-rings are going to be very cold. We've run some tests in the past few months that show the resiliency of the O-ring is very sluggish at low temperatures. It's very hard, and we would like to review that information. And I said yes, I will set up a meeting to review that information. We need to review the information and recommend whether we want to launch or what temperature we're willing to launch. I called Cecil Houston, who's a resident office manager of Marshall and Kennedy, and told him the concern, and he said fine, I'll get everyone on the network. He set that meeting up. The material was transmitted from Thiokol, and in that material was the data that we had on our erosion history and the fact that a year ago we did see some blow-by of the primary seals of the case joint. That was the lowest temperature we calculated the O-rings to be in the flight vehicle. That caused us some concern. We had also run some resiliency tests on the O-ring where essentially they were squeezed in between the plates and we removed it very rapidly and the pressurization motor would not respond. We were concerned about what impact this might have in low temperatures, and as a result of that, our recommendation at the time was not to launch below 53 degrees because we didn't know how much further below that we could go and be in the acceptable range. Was that ambient? That's what we calculated the temperature of the O-ring at launch a year ago because the local ambient temperature is actually higher than that. But if you recall, there were several days of very cold weather on that previous launch a year ago, and we calculated from that history what we thought the O-ring temperatures might be. That was on 51C? That's correct. What was that temperature? We calculated it to be about 53 degrees Fahrenheit in the O-ring area. And on this launch it was 29 degrees? Am I hearing you say that you recommended against launch and you never changed your mind? No, I did not say that. We did change our mind afterwards. What brought you to that decision? NASA concluded that the temperature data we had presented was inconclusive because the next worst blow-by we had ever seen in a primary seal in a case-to-case field joint was about the highest temperature we had launched at. We did have some data that indicated the timing function of the O-ring seal was going in the wrong direction, in the direction of badness. The O-ring was getting harder. The grease in there was getting more viscous. The time to seat the O-ring took longer and it would be more difficult to extrude it because of the hardened O-ring. We didn't know exactly where the right temperature were that would make it so it could not seal, but it was in the wrong direction. And the temperatures that were being reported for 51L were so much away from our experience base that we didn't feel comfortable operating that far away. We calculated, on the projected temperature that was given to us from the Cape, between 26 and 29 degrees Fahrenheit would be the O-ring temperature. In other words, to make it absolutely transparent to me, you're saying that you said, at least at that time, that you didn't want to launch if the O-rings were below 50 degrees, and secondly, you made an estimate, in view of the history of the weather, that the temperature of the O-rings might be as low as 26 or 30 degrees? That's correct, well below. So as far as 51L is concerned, 50 degrees was your first statement, and I'm going to find out what the change in their mind was in a minute. But there were two numbers that didn't match. The 50 that you said you shouldn't fly, and the distinctively below 50 they did fly. I still don't understand your explanation. Did you change your mind? Yes, the assessment of the data was that the data was not totally conclusive, that the temperature could affect everything relative to the seal. But there was data that indicated that there were things going in the wrong direction, and this was far from our experience base. The conclusion being that Thiokol was directed to reassess all the data because the recommendation was not considered acceptable at that time of the 53 degrees. NASA asked us for a reassessment and some more data to show that the temperature in itself can cause this to be a more serious concern than we had said it would be. At that time, Thiokol in Utah said that they would like to go offline and caucus for about 5 minutes and reassess what data they had there or any other additional data. And that caucus lasted for, I think, a half hour before they were ready to go back on. When they came back on, they said they had reassessed all the data and they had come to the conclusion that the temperature influence, based on the data they had available to them, was inconclusive and therefore they recommended a launch. When you say inconclusive, what does that mean? You told them the day before not to do it and now you've got some more data and you say it's inconclusive and so you changed your mind? I was not back at Wasatch when that discussion was being held. I was at Kennedy and I do not know what other data they were looking at other than the charts that I had in front of me and others had in front of them both at Kennedy Space Center and Marshall. I do know they came back on and said they had reassessed it and concluded that it was okay to launch, and at that point in time Thiokol was requested to put that in writing. Well, I think in the view of the very serious nature of this and the fact that it will be scrutinized for years that we should have precisely what the data was before we present it. Who made the decision from Thiokol? I do not know who made the final decision. I do know that the fax was signed by Mr. Joe Kilminster, my boss, the vice president. So there's no evidence that the evidence was looked at in this caucus that persuaded Thiokol that your first view was incorrect, that perhaps the first view wasn't based upon solid evidence? I cannot say specifically about that because I was not there to see it, and I think you would need to get people that were there at that meeting to discuss that. I'm sure you can see the logic of what you're saying. You recommended against a flight on one night, and then you have meetings with NASA people and they seem anxious to go ahead, or at least they were asking questions about it. And they give you some data and you check back with your home office and you got word to go ahead because the evidence is inconclusive. I believe, if I'm correct, he said that there was evidence of the low temperature in 51C where there was soot but no erosion. And you went back to the plant and talked to them, and subsequently they were looking around for other cases, if I understand what you said, and they found another case where there was soot, which took place in 75-degree temperature. So at this point the thing suddenly becomes less clear. Do I remember that correctly? That is correct. So that the additional data then was the discovery of 61A and leafing through the files, where they launched on a warm day and then they decided they didn't know. It is during McDonald's testimony that the Commission learns the true severity of the concerns the engineers had for that launch. The Rogers Commission would be focusing more heavily on the decision-making structure that led to those concerns being swept under the rug and its relevance in the decision to launch 51L. McDonald's surprise objection to NASA and Thiokol's management would put both of them under increased scrutiny. The next day's testimony would focus more heavily on the performance of the O-rings at the low temperatures experienced during Challenger's launch. Recognizing the connection between temperature and O-ring performance, Feynman had prepared a little demo for the managers. This morning we will start the meeting with officials from NASA, particularly dealing with the matter of seals on the booster rockets. This rubber thing that's put in, the so-called O-ring, that's supposed to expand to make contact with the metal underneath so that it makes a seal. Is that the idea? Yes sir, it should be in direct contact with the tang in the clevis of the joint and be squeezed 20/1000ths of an inch. And if it weren't there, if it weren't in contact at all and there was no seal at all, that would be a leak. Why don't we take the O-rings out? Because you would have hot gas expanding through the joint. Now, we couldn't put instead of this some sort of material like lead, that when you squash it, it stays? It has to be that it expands back, because there is a little bit of play in this joint and it has to be able to come back. I mean, it is a rubber material so that it comes back when you move a little and it stays in contact, is that right? Yes sir. Because when the seal moves a little bit, when there is vibration and pressures, it would lift the lead away, which the rubber expands in place. Yes sir. So it is important that it has this property of expansion and not be plastic like lead. And I think you call that resilience, right? That is correct. It has to have resiliency, and that's why we use an elastomer. If this material weren't resilient for say a second or two, that would be enough for a very dangerous situation. Yes sir. It is at this point in which Feynman starts his demonstration. He takes out a small O-ring of the same material that's in the solid rocket boosters. He also brought with him a small clamp. He had put one of the O-rings in a glass of ice water to cool it down and prepare the demo.
Oh, I took this stuff that I got out of your seal and I put it in ice water. And I discovered that when you put some pressure on it for a while and then undo it, it maintains, it doesn't stretch back, it stays the same dimension. In other words, for a few seconds at least, and more seconds than that, there's no resilience in this particular material when it's at a temperature of 32 degrees. I believe that has some significance for our problem.
This demonstration was a visual method of showing viewers the problems the O-rings start having at cold temperatures. The O-rings do not spring back into their original shape when cooled down. This became one of the most important moments in the testimony. The Commission had drawn a definitive connection between temperature and the performance of the O-rings. As it was the first time most of the public was being made aware of this effect, it was subsequently passed off as a discovery Feynman had made. However, both NASA and Thiokol were aware of this effect before they launched 51L. Thiokol's signed recommendation to launch 51L included a disclaimer that colder O-rings will be harder, and harder O-rings will take longer to seat. The discussion that occurred in the teleconference that decided to launch 51L wasn't trying to determine if O-rings became harder when they got colder. That was an already known phenomenon. The real controversy was centered around the fact that this effect might be severe enough to allow the internal pressure of the SRB to escape during the joint rotation that occurs during motor ignition. They were not being asked to determine simply whether cold temperatures made it unsafe to launch. They were instead being asked to provide a definitive temperature in which it became unsafe to launch. That would be significantly harder to quantify, especially with the very spotty data the engineers had to rely on at the time. Feynman's demonstration was a quick and visible example, perfect for the media to grab and show the public that this investigation was getting to the bottom of the cause of the explosion. The media, including his own website, presented as a discovery he had made when it was more of an observation. Nonetheless, it wasn't a good look for NASA that this information was coming from members of the Commission instead of themselves. The day's hearing continued with testimony from Richard Cook, who was there to answer questions about the memo he had leaked to the press. Mr. Cook, the Commission asked you to appear today because of recent stories concerning a memorandum which you wrote on the 23rd of July, 1985, and we will let you make whatever comments you would like to make on that memorandum. You told me before the meeting was reconvened that you would like to make some preliminary comments, and of course you may go right ahead and say anything you would like to. The memorandum in question I wrote very soon after my arrival at NASA. It was one of the first assignments that I was given, and it became apparent to me that there were some real concerns with the O-ring problem at that time, concerns from an engineering standpoint which had flight safety implications and potentially major budgetary concerns, because if you fix something like this, you've got quite a range of cost implications. It was mentioned that an effort was going to be made to keep the secondary O-ring from unseating in flight, or at least from breaking the seal in flight. Now the secondary O-ring, as I understand it, they started to discover that this joint rotation was unseating the secondary O-ring, and that was reducing or eliminating in some cases the redundancy feature on that joint. And so there was a lot of concern about how we could get redundancy back in that joint without having to throw away $500,000 SRB segments and starting all over again with redesigning and recasting them. And your focus of attention was primarily budgetary, is that correct? Yes, sir. I would like just to ask one question about the memo. You say at one point when you're referring to the engineers, I believe you say, these engineers have been improperly excluded from the investigation of the Challenger disaster. In light of the work of this commission and the investigations that are being conducted now at Kennedy, are you still of that view? Well, if I had access to my files and time to write, I would try to be more specific, that's all. But let me say this, the last item, frankly I was amazed that when this incident occurred, the engineers in Washington were over in their offices getting the data on the investigations from the newspaper and the media, and now and then phone calls from guys down at Kennedy about what was being found. These were the top propulsion engineers who prepared reports for the Office of Spaceflight and for the administrator and for us. I just couldn't understand why that group wasn't down there going through the data and looking through the photos and everything else. The only thing that I would urge would be as much as you can just to get the ordinary working guys, such as me and the engineers, and the guys from the Marshall S&E lab, and that's what I hope will be included. And I think that if everybody who has first-hand knowledge and experience feels that they can come up and talk freely, I think you will have a good investigation. Well, I assure you, Mr. Cook, we plan to do that, and we have plans made. The Commission would start asking the individual managers of their justification for launch. Now, could you give us, without being too precise, the nature of the arguments against launch? Tell us what was being said. There must have been a consensus against launch if that's what you conveyed to NASA. Well, at that point in time, we were trying to meet the deadline of getting the data together and getting the recommendation in, and so the engineering people were generating that and put together the charts. What were they saying, though? They were saying, we're going to be outside of our database to go colder than 53 degrees, and we're concerned about whether the O-ring will move fast enough to seat and seal before the joint opens up. And that was the thrust of the issue, is not knowing exactly how long it would take for the O-ring to move into position. Could I put the case and oversimplify it just a bit, because this is a good opportunity to be argumentative, if you will, on why you changed your mind. First, it was a criticality item 1, so that meant if it was a failure, the mission was a catastrophe, and there had been a discussion about that, a lot of it. Then you made a decision, you and Thiokol made a decision to recommend against launch for this very reason, that you were concerned. And then Mr. McDonald, in describing what happened, said that Thiokol had notified NASA that they should in effect not launch or conditions were not appropriate for launch, however you want to say it. And then there was a phone call, and he said, the conclusion being that Thiokol was directed to reassess all the data because the recommendation was not considered acceptable. And then you were supposed to have a 5-minute phone call caucus, which lasted 30 minutes, and you changed your mind. Now that, you know, is hard to explain it to an average outsider. You would think that it was one of the most critical things you can imagine in this program, and it had been so considered by NASA for a long time, and you obviously knew it. What caused you to change your mind? Try to explain it. The impression is that you were directed to do it, and there was so much pressure to get this launch off that you were directed to do it, and you did it. Now, if that's not the case, try to explain it in language that the public will understand. Why you changed your mind and how you did it so quickly. Well, I think I would start by saying that when we picked the 53-degree temperature, it was clearly the most conservative approach, and it was done because we had only gotten to a position in time to get to the telecon discussion. We had not established it as an unequivocal position, but rather one that was conservative, that stayed within our experience base. That was what we were thinking at that time. When we had the telecon, I would not characterize that NASA said directed us to reassess. What NASA said was, here is our feeling and our rationale, and we wonder whether you feel strongly that 53 degrees is as low as it is rational to fly. And I think we all recognize that it certainly was good at 50 degrees and 45, and so the question wasn't one of do you go below 53 degrees. It was a question of how much below 53 can you go. What data did you have to make that extrapolation? Did you have any data at all? Well, we had the effect of the temperature on the durometer of the O-ring. We had the one blow-by test that showed that it didn't blow by at 30 degrees. We had the ability to tolerate more erosion than we had ever had and still seal. But the reason for the debate was the fact that we didn't have hard evidence of how quickly that O-ring would move, and it became a matter of judgment rather than a matter of data, and that's the reason we couldn't reach a unanimous opinion. What was the split? How many people were against it, even at the last moment? We didn't poll everyone. Well, roughly. Well, I couldn't really guess. There were so many people. People were shuffling their positions within their own minds during the conversation. Roughly how many in engineering said they felt it was okay? Just from an informal poll, I would guess there were 5 or 6 the same way. So it's about evenly divided among the engineers? That's a very estimated number. Mr. Chairman, if I may make an observation, since the earliest days of the manned spaceflight program that I've been associated with and Mr. Armstrong has been associated with, our basic philosophy is, prove to me we're ready to fly. And somehow it seems in this particular instance we've switched around to, prove to me we are not able to fly. I think that was a serious mistake on NASA's part if that was the case. Mr. Chairman, I think I kind of understand all the details of this, but the gap that appears in my mind is the fact that we seem to have a situation where we are intended to have an operational vehicle that's going to fly on winter mornings for 20 years. And it should be able to handle conditions that are down around freezing, certainly if it's going to be operational in that category. And we have the mission rules, a launch rule that says it ought to be able to launch at 31 degrees or above. And yet we have seals that have constraints that are substantially away from what I would think would be a normal operating environment. They have to work very carefully to make sure that, in fact, this critical system was going to operate well within what I would think would be an operating envelope. If I don't understand that right, I would like to have somebody tell me why that doesn't characterize the system. In fact, there weren't any specific constraints on the O-ring temperature, specific to the O-ring. Well, that's one of the things I don't understand, because I guess I agree with Cripp, that the NASA philosophy is it's supposed to be proved to me that it works under these conditions. And as far as I can see, there's no data and no tests that give you any confidence that the joint would be expected to operate at 31 degrees. I mean, maybe it does, but there's no data that proves that. Now it was time for the engineer's testimony. I felt we were very successful up until early evening, because it culminated in the recommendation not to fly, and that was the initial conclusion. I was quite pleased with that. I presented and prepared charts, and basically those were the charts where I had that exaggerated view showing the O-ring and joint rotation. I was basically concerned with how low temperature affects the timing function and ability of the seal to seal. Low temperature, and I stated this for over a year, is away from the direction of goodness. I cannot quantify it, but I know that it's away from the direction of goodness. I feel very strong, and I always have felt very strongly, that SRM-15 was telling us a message. And at the flight readiness review, we did not have any data to support anything but a generalized statement that said we feel that temperature was a contributor. On the net that night, after I presented those feelings very strong, I get very emotional about these things, and I was quite strong over the net about it, as George Hardy remembers. Somebody brought up about SRM-22. Gas blowby that was observed on that was gray, splotchy type blowby over a specific arc length. I made that point that on SRM-15 we had over 100 degrees of arc, and the blowby was absolutely jet black. But we had analyzed that chemically and found the products of combustion in it. We found the products of putty in it, and we found the products of O-ring in it. I made that point. I was asked then on the net to support my position with data, and I couldn't support my position with data. I had been trying to get data since October on O-ring resiliency, and I did not have it in my hand. At that point, the telecon basically continued, and Mr. Lund presented his conclusions and recommendations. So the formal part of the presentation was finished. Listeners on the other line seemed not very pleased with the recommendation. In fact, somebody asked Mr. Hardy what he thought about it, about our recommendation, and Mr. Hardy said he was appalled at Morton Thiokol's decision. However, he would not go against our recommendation not to fly. There was a very short discussion that ensued. Our people asked for a 5-minute caucus to discuss the situation. Those opposed to launching continued to press their case with Morton Thiokol management, and those opposed to the launch that pressed this case in the caucus were basically myself and Mr. Thompson. And we did everything we could to continue to try and press for not launching. I took the photographic position of the evidence, and Mr. Thompson was trying to further elaborate on the sealing characteristics of the seals. When we realized that we basically had stopped in the discussion and we could go no further because we were getting nowhere, we backed off, both of us. We just sat back down. What was the motivation driving those who were trying to overturn your opposition? They felt that I had not conclusively demonstrated that there was a tie-in between temperature and blowby. My main concern was if the timing function changed and that seal took longer to get there, then you might not have any seal left because it might be eroded before it seats. I just don't know how to quantify that. but I felt that the observations made were telling us that there was a message there telling us the temperature was a discriminator, and I couldn't get that point across. I basically had no direct input into the final recommendation to launch, and I was not polled. I think Astronaut Crippen hit the tone of the meeting exactly right on the head when he said that the opposite was true of the way the meetings were normally conducted. We normally have to absolutely prove beyond a shadow of a doubt that we have the ability to fly, and it seemed like we were trying to prove that we had data that we couldn't fly at this time instead of the reverse. That was the tone of the meeting in my opinion. The commission would turn their attention back to the managers who seemingly ignored the engineers' concerns. But the thing that's most troubling to me is if you had Mr. Thompson, who is a supervisor, and he says all of his people had doubts about whether this launch should take place, what was it that caused you to go ahead and approve it? Well, let's see. First off, to say that all of his people didn't even know that there was an issue, and so I mean, it's really conjecture to determine what their position would have been. But as far as what motivated us, it was logic that said that 53 degrees is not a threshold. If you ask anybody, would 50 degrees be okay, I think everyone would sign up at 50 degrees. So every flight which the program has had has to break some frontiers. But when you go from STS-1 to STS-2, you went into a temperature regime that you weren't in. And so as you move down through the program, you're working to some degree in an extrapolated area. The time you go through frontiers is during testing, not during the flights. That's the way it's supposed to work. Well, demonstration is a better word. At the demonstration, you fall on your analysis when you make your first flight, and your second flight you're falling on your analysis. You have not demonstrated everything that you're going to see. I hope that's clear. I'm trying to say that when we qualify in the first place, we don't test the full range of every piece of item, and we therefore take some data and extrapolate it by analysis. So we don't have actually demonstrated capability on every facet of the motor. We're talking about 25 degrees away from your experience. And that's certainly the reason that it had the extensive debate that it did. We're always working somewhat in the extrapolated area. But that is not this case. I mean, here you have a lot of warning, and you've been discussing the O-rings and seals, and you've all had concerns, and it's all over the papers. All you have to do is look at it, as we have, and you can see that it's been a major concern. And now you have a situation where there's a lot of concern, and a lot of your people expressed a negative vote, and that our people in NASA don't even know about it. I mean, that's unbelievable to me. At least if there were a calculated decision and everybody says yes, we all know about it and we're willing to take the risk, and there is some risk, and I suppose you have to do that. Every flight has some risk, but this one seems so difficult to explain. I have one question. I'm really confused as to whether the secondary seal was considered by anybody to be effective or not. But the statement that was used states if the primary seal does not see, the secondary seal will see. I think that is a key issue. What the hell is going on there? Did the people know that stated that criteria? Did they know this? And why didn't Morton Thiokol and NASA have better communications on that very critical item? I just don't understand it, and I've listened for 2 hours and I still don't understand it. I think I hear two different things here. It's sort of a hell of a way to run a railroad on a critical item like this. The hearings were ending in an increasingly sour direction for NASA, Marshall, and the managers at Thiokol. Together, they decided to start holding practice hearings with attorneys they had paid on both ends. These practice hearings would give NASA management an opportunity to run through any possible questions the commission might ask. The managers would then receive advice from the attorneys how to best answer the questions for when the real hearings continue. McDonald and the engineers were invited to join. Throughout the course of these hearings, the attorneys had made it very clear that nobody should volunteer information. Everyone on the stand should take the same strategy one would use if they were a defendant in a criminal case. Answer only the commission's question with a yes or no and provide no more information than is absolutely necessary. You must tell the truth, but don't elaborate on the answer, as it may be misconstrued later, which could cause you some problems. McDonald had significant reservations with that strategy. He was aware the commission already felt NASA weren't being upfront about the information they should be. Now that Morton Thiokol was also being instructed to follow that lead, he felt he needed to speak up. I do not agree that it would be in the best interest of the company or the employees testifying tomorrow to respond to the commission as instructed. It is my intent tomorrow to tell the commission everything I know about the circumstances leading up to the accident in as much detail as I can remember. By doing so, I hope that I'll never have to appear before them again and respond to the question, "Why didn't you tell us about that when you were here before, Mr. McDonald?" With this statement, he had officially separated himself from the party line. Boisjoli joined him in his stance against the advice of the attorneys and Marshall management. I agree with Al, and I'm going to do the same thing. The meeting broke up on a sour note, and Marshall management continued planning with the attorneys. They were preparing a pre-made presentation. They were coordinating their testimony in such a way that they would be the first ones to set the story and allow information to be passed to the commission. In order, Malloy would give a timeline overview, Mason would provide reasoning for the decisions, Lund would respond to the engineering recommendations, and then Kilminster would provide the final reasoning for launch. McDonald and the engineers would only then be allowed to testify. At the closing of this meeting, Malloy was reported to have said, "Looks good if McDonald doesn't throw another turd on the table." Much to the dismay of the managers, the Rogers Commission had published the order in which they will take the stand. The commission was apparently surprised enough by his unexpected introduction that McDonald would now be taking the stand first. When Mason found out about this, he was appalled. "It's been my understanding that you all had pre-coordinated our agenda with the legal counsel for the Presidential Commission and that they had accepted our plan, which has me testifying first and McDonald testifying last. Get on the telephone right now and get this whole thing straightened out because this is the way we're going to proceed tomorrow." A representative from the commission responds to Mason's call. Chairman Rogers plans to proceed on the schedule that was released to the press. If Morton Thiokol management has some overriding reason why this isn't appropriate, Chairman Rogers would be more than happy to meet with them in closed chambers tomorrow morning a half hour before the scheduled hearings. He told his attorneys to start preparing for that meeting. A frustrated Mason walks out of the private meeting with the commission. He tells McDonald, "You will be testifying first." The hearings begin, and McDonald is asked about his recollection of the teleconferences. There was an exchange amongst the technical people on the data as to what it meant and discussions. But the real exchange never really came in until the conclusions and recommendations came in. At that point in time, our Vice President, Mr. Bob Lund, presented those charts, and he presented the charts on the conclusions and recommendations. And the bottom line was that the engineering people would not recommend a launch below 53 degrees Fahrenheit. Well, that temperature brought a lot of strong comments and a reaction from several of the NASA officials. I believe it was Mr. Malloy that made some comments about when we will ever fly if we have to live with that sometime in the future, and also commented that we're trying to establish a new launch commit criteria and we can't do that. You don't do that the night before a launch. That is a predetermined set of constraints and we can't do that. And other comments were made about whether we could ever fly out of Vandenberg 24 flights a year because it wasn't uncommon to have 53 degrees in the early morning hours where a lot of the launches occur. One of the comments that came from Mr. Hardy at Marshall Space Flight Center was that he was appalled at that recommendation. However, he said that he certainly wouldn't fly without Thiokol's concurrence. I believe it was Stan Reidarts that made a comment that he was under the impression that the solid rocket motors were qualified from 40 to 90 degrees, and that 53-degree recommendation certainly was inconsistent with that. Could I ask you to stop there for a moment and go back? We will come to the caucus in a minute, but go back and explain what was said to convey the decision of no launch. I gather at that point the decision by Thiokol was to recommend against a launch? That's correct. The recommendation was not to launch below 53 degrees. Who did the talking on that subject? That was Bob Lund, Vice President of Engineering, who presented that position. Were you able to ascertain from that conversation how the engineers as a group stood on that? I can't speak for the group, I was not there, but I did hear the engineers that presented the charts that supported the 53-degree recommendation. And I felt they were very strong in their conviction as to why they felt uncomfortable to go outside that experience base. And who were they? Roger Boisjoli, I think, was one of the strongest ones, and Arnie Thompson that presented those charts. And Mr. Lund himself at the time? Yes, Mr. Lund himself at the time didn't present the detailed technical charts, but he did present the conclusions and recommendations, and that was his recommendation as Vice President of Engineering. Was anyone who was on the telecon from Thiokol's side recommending launch? At that time, no, there was no one that recommended launch. Mr. McDonald, I have one question. Before you went off the net, did you ask or make a comment about the secondary O-ring seal seating? I made the comment that lower temperatures are in the direction of badness for both O-rings because it slows down the timing function, but the effect is much worse for the primary O-ring compared to the secondary O-ring because the leak check forces the primary O-ring into the wrong side of the groove, while the secondary O-ring goes in the right direction. And this condition should be evaluated in making the final decision for recommending the lowest acceptable temperature for launch. That was the comment I made. That confused some people. Some of the witnesses I spoke to thought that that was a comment in support of the launch, the fact that the secondary O-ring seal would seed. Well, that comment is a good news, bad news comment. There's good news and there's bad news. The good news is that the secondary seal is in the right position, but that is not unique to temperature. It is always that way. The bad news is that the primary seal is the one that we are depending on for the full ignition transient, and it's going to be a lot worse than it was. But even the secondary, as I mentioned, wouldn't be as good cold as it would be normally. But by this comment, you were not supporting the launch? No, not by that comment, I wasn't supporting the launch. I was just saying it's an important consideration, and I felt that if we could run some calculations to show that the temperature did not affect the timing, then that would be supportive of the launch. If it did, and that was a concern, if we pushed that timing out long enough, we had a chart in there that said if the timing goes beyond that 200 psi regime while you're still eroding that primary O-ring, that for whatever reason you ever bypass it at that time, you can't depend on that secondary. And that's what is important. So at the time of the caucus then, you never favored launch? No. Would you be surprised if your comments were interpreted by both your own company and personnel and Marshall personnel as being supportive of the Marshall position? Yes, I would be surprised at that. I wouldn't be surprised that that would be evaluated as the effect of that, but I would be surprised that it was interpreted as supporting. If we may now, let's go back. You said that a suggestion was made that you have a recess for 5 minutes. Who made that suggestion? That suggestion was made from someone at Thiokol. I think it was probably Joe Kilminster, but I'm not sure. Okay, now what happened? You said that that lasted almost a half an hour instead of 5 minutes? That's correct. And during that time, what did you do and who were you with? I was in the conference room at Kennedy with Mr. Reinhardt and Malloy. I commented at that time that I suggested that maybe we consider a late afternoon launch. Based upon the weather report I heard, the temperatures would be 48 to 50 degrees in the late afternoon. So I said, why don't we go to a late afternoon launch? And I was told that that was considered, but it was rejected because of some problem either with visibility or weather at one of the transatlantic abort sites. And the reason it was taking so long for this 5-minute caucus is that we were either trying to find some more information to support our recommendation or that we were trying to run some kind of calculations to determine how far away from that we could go. Because clearly 26 degrees is a long way from 53. And finally, the people from Thiokol in Utah did come back on the line after about a half an hour. And I believe it was Joe Kilminster who came back on the line and said that, even though we had some concerns about the lower temperatures, that we would recommend that they proceed with the launch, based on the fact that we felt the temperature data that we had was not totally conclusive. When he completed that, he was asked to put the rationale in writing and to sign it. And I was sitting across the table from Larry Malloy at the time, and I said I felt that I was the one who was going to have to sign it, because I was at the Cape, and I said I wouldn't sign it. I couldn't. It would have to come from the plant. I told him I didn't feel very good about this recommendation, and I recognized it's very difficult to quantify at which temperature these seals may be acceptable, and where they aren't acceptable based upon that data. Some of it certainly was inconclusive, there was no doubt in my mind, and that's a difficult thing to quantify. But even though I didn't agree with the 40-degree qualification of the motor, that all elements were qualified to that, it was my understanding that there were a lot of people at both NASA and Thiokol signed up to that, and I was absolutely surprised that NASA would accept any recommendation below 40 degrees Fahrenheit, especially when the predicted temperature was as low as 26 degrees Fahrenheit. In fact, I made the direct statement that if anything happened to this launch, I told them I sure wouldn't want to be the person that had to stand in front of a board of inquiry to explain why we launched this outside of the qualification of the solid rocket motor or any shuttle system. One other question. Dr. Keel asked at the conclusion of your testimony in executive session whether you felt that you were under pressure or the company had been under pressure to reverse its decision, and I think your answer was yes. Do you remember that? Yes, definitely. There was no doubt in my mind. I felt some pressure. I feel that I have a responsible management position, and I felt pressure. Would you explain the reasons for feeling pressure? Well, I've been in many flight readiness reviews, probably as many as anyone, in the past year and a half at Thiokol. And I have had to get up and stand before I think a very critical audience at Marshall, and a very good one, justifying why our hardware was ready to fly. I have to get up and explain every major defect and why we can fly with that defect. And for the most part, they're very minor, very, very minor. And I've been hassled about how I'm sure that's okay to fly with. You know, such things as losing vacuum in a carbon cloth part in the nozzle while the part is basically cured. It's a critical process. There are a lot of those critical processes, and I have to address every one of those in great detail as to why I am sure that part has not been compromised. And it's been that way through all of the reviews I've ever had, and that's the way it should be. And it's not pleasant, but that's the way it should be. And I was surprised here at this particular meeting that the tone of this meeting was just the opposite of that. I didn't have to prove that I was ready to fly. In fact, I think Bob Crippen made the most accurate statement I ever heard. His conclusion from that meeting was the philosophy seemed to have changed because he had the same impression I did. That the contractor always had to get up and stand up and prove that his hardware was ready to fly. In this case, we had to prove that it wasn't, and that was a big difference. I felt that was pressure. And can you explain a little more what source the pressure came from in your mind? Well, I think the strong statements that were made by Mr. Malloy and Mr. Hardy were I think fairly strong statements that I took as pressure about when we will ever fly this thing. And the launch commit criteria that we can't generate at the last minute, and appalled by our recommendation to fly at temperatures as high as 53 degrees. And that to me, that was pressure to me. It may not have been interpreted by others, but it was pressure to me. And as I recall in your testimony, you testified that you made it clear that you would not sign a written statement approving the launch. Am I correct? Yes, that's correct. And I think that has been misinterpreted, at least by the press. They said that I was overruled by my supervisor. That's not true at all. I chose not to sign that. He didn't overrule me. I felt that that decision, when I started, was an engineering decision by the people that understood the problem the best, that had all of the data and facts, and they were the ones who should recommend it. And that's why I made that. It wasn't that I was overruled. Mr. McDonald, you mentioned earlier that you thought this decision on launching should be an engineering decision and not a program management decision. How would you characterize the final decision to launch from Thiokol? Was it engineering or was it management? I guess I would have to characterize it as a management decision. Were you surprised that some of the top people in the decision-making process didn't know about this at all? The concern on your part and on the part of Thiokol's engineers that the original decision had been not to launch and all of that. I'm very surprised at that. I hardly believe that. The issue was so controversial, I thought that I'm sure that they were aware of it. I have a hard time believing they didn't. The commission then moves to questioning the managers. Out of that discussion, we got to the point where we couldn't make a clear conclusion of the effect of temperature on the O-ring performance. And a number of the engineers felt on that basis we ought to stay where we were in their flight history, and with the information we had at that point, and as far as we had proceeded in our thought process, that appeared to be the right thing to do. And so we proceeded to present that information. Isn't it fair to say, though, that all of the engineers felt that way? No, sir. Which one's favored? At that point, it was not a pro-con sort of discussion. Where we were in our thought process was let's stay with our experience. But what I mean is, didn't all the engineers agree with that? I would say that at that point we all agreed with that it wasn't engineering or anyone else. We had just looked at what we had and we went through our thought process, and at that point we felt that that was the recommendation that we got. The position though that you took unanimously was the engineering position, was to base the recommendation on previous flight history, and you cite 51C, which was the coldest launch that had been made and where you had the most trouble, isn't that right? That's right. The next comments then were essentially, as Mr. McDonald said, that Mr. Malloy said he disagreed because he didn't feel that we had shown any correlation between blow-by and erosion with temperature. And Mr. Hardy expressed surprise at the recommendation because it was above our qualification temperature. However, he said he wouldn't recommend flying against our recommendation. And then Mr. McDonald came on and said that he too had a concern about the cold, and he pointed out that the secondary O-ring was in the position to seal, and that this point ought to be considered. With that discussion, we felt that we needed to have further discussions to see if these comments would in fact cause us to have any change in our position. And so we decided to do that off the net, and we asked for a caucus. Now in the caucus, we revisited all of our previous discussions, and the important things that came out of that was that, as we had recognized, we did have the possibility that the primary O-ring might be slower to move into the seating position, and that was our concern. And that's what we had focused on originally. The fact we couldn't show direct correlation with the O-ring temperature was discussed, but we still felt that there was some concern about it being colder. Could I ask a question? Your engineers, with the data they had and with the concern with the temperatures, did reach a tentative conclusion, at least that, why not wait for at least a temperature that had already been flown? Well, let's say the request to reassess was not a major factor in my view. The fact that we were picking a temperature based purely on one test or one flight, it was difficult to say that 53 degrees was exactly the temperature that you ought to fly at. And when Mr. McDonald made the point about the secondary O-ring being in a favorable position, we felt that it was appropriate to consider that point. And that's the reason we said, well, let's make sure that we have considered everything. And the two things that came out of that assessment were, one, that we believed that we had a substantial margin of allowable erosion and still have that primary O-ring seat and seal properly. And so under those conditions, if you were to have blow-by, you would be seating the secondary. In any event, we did expect the primary to seat. We expected it to seat because we had some tolerance of its ability to erode and still seat and seal. And so that was our thought process. At that point, it was clear to me we were not going to get a unanimous decision. And so the question was, did we have a reasonable position to go to 53 degrees, or did we have confidence that we could fly with a 29-degree O-ring? And the people who were there had heard all of the discussion, and so I concluded it was appropriate to get a poll of the chief engineer and the chief program manager and Mr. Wiggins, who has the division responsibility, to see how they felt, whether they felt that we could safely fly with all of the information that had been presented. And we did conduct that poll, and we did conclude that it was safe to launch. Could you tell us what the poll showed? You say that you and Mr. Kilminster and Mr. Wiggins and Mr. Lund were unanimous. How about the others? We only polled the management people because we had already established that we were not going to be unanimous. That wasn't the question. The question was about the others. You testified before that you thought probably all of the engineers were against the launch, and now you say you took a poll and you only polled the managers. You didn't ask the engineers how they felt after the review of the data? In that discussion, I felt that everyone had represented their opinion. Did they express a change of mind? Did they say, well, I've changed my mind? Not per se, no. Excuse me, I just feel that this is the kind of discussion that we frequently have, in which all of the people express their opinions and they make them clear. Did you ever have an experience where all of the engineers voted one way and management voted the other? That wasn't the case here. What was the case here? It looks that way. It looks as if you said the managers you pulled were unanimous and the engineers who were opposed to the launch were still apparently opposed to it. There were some engineers. Which ones? Mr. Boisjoli and Thompson were the outspoken ones. I'm asking which ones changed their minds. Before, you testified that all the engineers were opposed to the launch, and now you went through this process you've just described to the commission. What we were faced with was that there were the outspoken individuals, and the rest participated to a lesser degree. But I believe that we are familiar enough with the people and their manner to be able to judge their feelings, and we heard what they had to say. Mr. Mason, earlier in testimony in private session, you indicated that Mr. Boisjoli and Mr. Thompson were the most knowledgeable on the seals. Is that correct? Yes. Then the two most knowledgeable engineers were still opposed, and my understanding is they were still strongly opposed. Why did you proceed in the light of your two experts being very strongly opposed? I would say that we felt that, although they were outspoken, we listened to their reasons more than the intensity, and the reasons boiled down to the things that I said. The reason was the uncertainty about the rapidity with which that primary would move. I have a question about the temperatures. You said that you decided that 29 degrees was safe to launch. Did the discussion result in some lower temperature limit below which you would not have recommended a launch? We didn't pursue the idea of getting any colder than 29 degrees. Well, how critical was this? If the temperature turned out to be 28 degrees, would this have made a big difference? The recommendation was based upon a prediction. Of course, that was only a prediction at the time, and you didn't know exactly what the weather was going to do and exactly what the temperature was going to be. And I would have thought that the recommendation would have been more specific, so that depending on the exact conditions which prevailed when the launch occurred, the recommendation would have been one which could have been used to make a decision. Well, I can't argue with that reasoning. We were addressing the specific condition, not looking for a threshold. But usually engineering decisions and calculations are pretty exact calculations, and you usually have a very specific number. And that's why they are launch criteria, and those numbers are specific numbers, they are not ranges. And here evidently you had a range, but you didn't even specify what that range was. Wasn't that rather unusual? Yes, I would say it was, the fact that we were focused on that one point, and that's what we were addressing. We were faced with, we felt, a specific condition here, and that's the reason we addressed it that way. So you didn't feel uncomfortable with this position? I didn't. I felt that, after we had hashed it out and understood it, that the inability to precisely quantify the movement of that primary O-ring was the concern that we had. Mr. Mason, you've used the word uncertainty now 4 or 5 times in the last 5 minutes, and now you've just had the inability to quantify this thing. I mean, every launch has a risk, but you take that risk because something must be achieved. What was driving here? What was to be achieved that caused you to go? Why couldn't you wait a day? Well, as far as waiting a day is concerned, we wouldn't have gained any more information. You would have gained temperature. Mr. Mason, in responding to the general's questions about the use of the word inconclusive and uncertainty in your whole presentation here today, you were basing your decisions on inconclusive and uncertain information. And yet, my understanding of NASA's flight philosophy is that decisions to go or no go are based on certainties and conclusions. When did this change in philosophy affect your operations? Well, I would have to respond. I think it's a case of degree of uncertainty. Well, do you allow any degree of uncertainty before you launch? I believe that in any case in the design and testing and so forth of the whole system, there have to be some uncertainties. It is a question of degree. But it seems to me there was a high degree of uncertainty in your calculations here. Well, that's of course the point that we were struggling with that night, was what degree of uncertainty is there. And the area of uncertainty was the moving of the primary O-ring. Well, how would you characterize it? A high degree, a low degree, or a medium degree of uncertainty? As far as the probability of seeding is concerned, I thought that there was a low degree of uncertainty. Following up on that, Mr. Mason, Mr. Kilminster, when he wrote the telefax, said, temperature data not conclusive on predicting primary O-ring blow-by. Isn't that a very serious statement, saying that it was not conclusive? Isn't that another way of saying that there might be a conclusion that there was going to be primary O-ring blow-by? Well, what we did say, since it wasn't conclusive, we were going to assume that it would have a negative effect. That's the way we approached it. In other words, this is a statement saying we expect primary O-ring blow-by. We said we can't tell how much effect temperature is going to have, and so we had better look at what can happen if it in fact does. Mr. McDonald stated that he did feel some pressure. Do you think schedule pressure or cost pressure had significant influences in this instance? Cost pressure definitely had no bearing on it. From a schedule standpoint, we take a lot of pride in the fact that we have supported all of the launches to date, and if there was any pressure, we wanted to continue to do the job we had been doing. And that kind of situation exists every time. We have to say, are we ready to fly or are we not? And we want to be ready to fly, but we want to make sure it's safe. Mr. Mason, when you spoke of Mr. Lund and told him in effect to take off his engineering hat and put on his management hat, wasn't that pressure on your part to a subordinate that he should change his mind? Well, I hope not, but it could be interpreted that way. Now it came time for the engineer's testimony. Mr. Boisjoli, on 51C, you saw a very blackened joint. 2 of them. Well, however, on 61A, the temperature was 75 degrees, and that has been used to minimize the effects on 51C, saying that it occurs at warm temperature also. Would you explain the difference that you saw or heard between the 2 joints? Yes, the SRM-22 that was used as a comparison basis was not one that I saw personally, but a junior engineer had actually been at the Cape and saw those joints. Then we discussed the photos. He had a photo of that joint, and I had a photo package of the SRM-15, and we put the photos side by side. And you could see that the SRM-15 joint had coal black color where we had photographed it, and the joint was as he described. It was not coal black. It was significantly lighter and a little bit splotchy. The splotchiness wasn't so definitive, but that's how he defined it to me. Now on that basis, I concluded, and so presented the night before the launch, that that was extremely significant. It was very significant because it was telling us that temperature was indeed a discriminator. Each person during the telecon presented their own charts. I expressed deep concern about launching at low temperature. Basically, if erosion penetrates the primary O-ring seal, there is a higher probability of no secondary seal capability in the steady state condition. Others in the room presented their charts, and the main telecon session concluded with Bob Lund, who is our Vice President of Engineering, presenting his conclusions and recommendations charts, which were based on our data input up to that point. Listeners on the telecon were not pleased with the conclusions and the recommendations. What was the conclusion? The conclusions were that we should not fly outside of our database, which was 53 degrees. Who presented that conclusion? Mr. Bob Lund. He had prepared those charts. It was about that time that Mr. Hardy from Marshall was asked what he thought about the Morton-Thiokol recommendation, and he said he was appalled at the Morton-Thiokol recommendation. Mr. Hardy was also asked about launching, and he said no, not if the contractor recommended not launching. He would not go against the contractor and launch. There was a short discussion that ensued about temperature not being a discriminator between SRM-15 and 22, and shortly after, Mr. Kilminster was asked by NASA if he would launch, and he said no because the engineering recommendation was not to launch. Then Morton-Thiokol management then asked for a 5-minute caucus. We put the line on mute and went offline for the rest of the net. Mr. Boisjoli, at the time that Thiokol made the recommendation not to launch, was that a unanimous recommendation as far as you knew? Yes, I have to make something clear. I have been distressed by the things that have been appearing in the paper and things that have been said in general. And there was never one positive pro-launch statement ever made by anybody. There have been some feelings since then that folks have expressed that they would support the decision, but there was not one positive statement for launch ever made in that room. So we spoke out and tried to explain once again the effects of low temperature. Arnie actually got up from his position, which was down the table, and walked up the table and put a quad pad down in front of the table, in front of the management folks, and tried to sketch out once again what his concern was with the joint. And when he realized he wasn't getting through, he just stopped. I tried one more time with the photos. I grabbed the photos, and I went up and discussed the photos once again and tried to make the point that it was my opinion from actual observations that temperature was indeed a discriminator, and we should not ignore the physical evidence that we had observed. And again, I brought up the point that SRM-15 had a 110 degree arc of black grease, while SRM-22 had a relatively different amount, which was less and wasn't quite as black. I also stopped when it was apparent that I couldn't get anybody to listen. At this point, did anyone else speak up in favor of the launch? No sir, no one said anything. In my recollection, nobody said a word. It was then being discussed amongst the management folks. After Arnie and I had our last say, Mr. Mason said we have to make a management decision. He turned to Bob Lund and asked him to take off his engineering hat and put on his management hat. From this point on, management formulated the points to base their decision on. There was never one comment in favor, as I have said, of launching by any engineer or other non-management person in the room before or after the caucus. I did not see the final version of the chart until the next day. I just heard it read. I left the room feeling badly defeated, but I felt I really did all I could to stop the launch. I felt personally that management was under a lot of pressure to launch and that they made a very tough decision, but I didn't agree with it. One of my colleagues that was in the meeting summed it up best. This was a meeting where the determination was to launch, and it was up to us to prove beyond a shadow of a doubt that it was not safe to do so. This is in total reverse to what the position usually is in a pre-flight conversation or a flight readiness review. It is usually exactly opposite of that. Do you know the source of the pressure on management that you alluded to? I felt the tone of the meeting was exactly as I summed up, that we were being put in a position to prove that we should not launch rather than being put in a position to prove that we had enough data to launch. And I felt that was very real. I take it you were asked to prove that the seal would fail? Yes. And of course you couldn't, because as a matter of fact it didn't. That is, 5 of them didn't, and only 1 of them did. And if you had proved that they would have all failed, you would have found yourself incorrect and under criticism because 5 of them didn't fail. That is right, I was very concerned that the cold temperatures would change that timing and put us in another regime, and that was the whole basis of my fighting that night. Is it just that the probability had been increased to a point where it was intolerable? That's right. It was now Bob Lund's turn to take the stand. How do you explain the fact that you seemed to change your mind when you changed your hat? I guess we would have to go back a little further in the conversations than that. We have dealt with Marshall for a long time and have always been in the position of defending our position to make sure that we were ready to fly. And I guess I didn't realize until after that meeting and after several days that we had absolutely changed our position from what we had been before. But that evening, I guess, I had never had those kinds of things come from the people at Marshall that we had to prove to them that we weren't ready. And so we got ourselves in the thought process that we were trying to find some way to prove to them it wouldn't work. And we were unable to do that. We couldn't prove absolutely that that motor wouldn't work. In other words, you honestly believed that you had a duty to prove that it would not work? Well, that's kind of the mode we got ourselves into that evening. It seems like we have always been in the opposite mode. I should have detected that, but I did not, but the roles kind of switched, and so after making, or listening to the verbal presentation in the afternoon, they had asked what Thiakol's position was, and I looked around the room, and I was the senior person, and I said I don't want to fly. It looks to me like the story says 53 degrees is about it. And of course, we were requested to then go back and do something more and prepare detailed charts to show that in more detail. So it was in a real-time mode, and we were trying to absorb the data and put together the story. Well, as a result of that telecon, I gave the charts that made the recommendation that we wait until the motor got to 53 degrees. I didn't see anything different that I hadn't seen before, and of course, you have heard the story of what happened after that. Did you, as the supplier of the system to the government, have a specification on the O-ring temperature, or could the O-ring temperature have been anything? I don't believe there is a specification on the O-ring temperature other than the material itself, but it doesn't specify the operational aspect, does it? To my knowledge, no. In fact, the mil-spec says specifically that the O-ring should be qualified for whatever uses they're put to. So did you take any steps to do that? That is, qualify the range of temperatures over which these O-rings were to be used? Yes, the development motors were fired from 40 to 84, and the qualification motors from 45 to 83. So then 40 degrees was the temperature limit for the O-ring? In the full-scale qual program, that is correct. So when it was predicted that the temperature of the O-ring at launch of 51L was going to be 29 degrees, the O-ring was outside of the qualification temperatures by some 10 degrees. That is correct. Then how could you make a recommendation to launch if you were 10 degrees outside of your qualification? Our original recommendation, of course, was not to launch. Well, I understand that, but your final recommendation was to launch. Okay, what we need to do then is go through that rationale. Well, I think we have heard what explanation you've given. I think the problem we're having is it is not convincing. I mean, if you don't mind, I assume you have great confidence in your engineers, Boisjoli and Thompson, and the others. And they are probably as well qualified as anybody in the country in dealing with these problems of O-rings and seals and so forth, is that right? Yes. And you had a long discussion in the telecon, and you decided, all of you, I understand, all of you decided that for safety reasons you would oppose the launch. And thereafter, NASA, in one way or another, made it clear that they were displeased with that recommendation. And I assume that you knew when you made the recommendation that your recommendation in fact was going to determine whether that shuttle would be launched or not, because NASA had indicated to you that they would not fly unless they had a written report from Thiokol saying you approved the launch. I didn't know NASA would accept that. You didn't know that? No. Well, you must have known your recommendation was very important. You knew that if you voted against the launch, it would not have been launched, didn't you? Well, we had voted prior to it, and they didn't accept it, so I couldn't forecast what NASA would do. But you knew that that was the reason they asked you to reconsider. That is why you had the 5-minute recess, didn't you? That's a fair statement, yes. Now, knowing that, and knowing that the safety of the crew was involved, and knowing your own people, the engineers that you respected, were still against the launch, what was it that occurred in your mind that satisfied you to say, okay, let's take a chance? Well, I didn't say take a chance because I felt there was some rationale that allowed us to go ahead. Well, maybe that isn't fair. Then what was it that occurred in your mind that caused you to be willing to change your mind? I guess one of the big things was that we really didn't know whether temperature was the driver or not. We couldn't tell. We had hot motors that blew by and cold motors that blew by, and some very near either end that did not. The data was inconclusive, and so I had trouble justifying in my own mind and saying, by golly, temperature is a factor. I have great difficulty with this. In the usual practice, when there is any real doubt about flight safety, whether it is aircraft or whatever, you simply don't fly. And it seems to be that this is the reverse. And I just have great difficulty understanding the question that has been asked before. I just haven't heard as to why, if there is any doubt in your mind, why you went ahead. Why you changed your mind. I just don't understand it. And I would appreciate very much if you could explain that. Maybe we ought to go to Mr. Kilminster if you don't mind. He signed the telefax, and we have asked Mr. Lund a lot of questions, and I think maybe in fairness to Mr. Lund, Mr. Kilminster, could you attempt to explain to the Commission why I guess you changed your mind too, didn't you? Yes, sir, based upon the discussion that we had and the rationale that was developed. How can you say you changed your mind when you say temperature and data not conclusive on predicting primary O-ring blow-by? Did you have a feeling that the burden of proof was on you to show that it wasn't safe? No, I think we were asked to relook at the data, which we did. Mr. Kilminster, did you have any feeling of pressure being put on you by NASA, or were you just calmly reassessing? I felt that the pressure that was put on us was to go back and look at the data, look at the detailed information that had been presented to see if there was something that we were seeing that we were not representing on the phone. You didn't feel they were trying to get you to change your mind? I did not feel a significant amount of pressure in that regard. Due to McDonald's testimony, he would receive a call from Wiley Bunn, the director of the Reliability of Quality Assurance Office at Marshall, warning him that he may face retaliation for exposing Marshall management. Mr. McDonald, I don't mean to scare you, but I've heard some talk around here that leads me to think that Marshall management may be plotting against you. If I were you, I'd watch your backside. McDonald and the engineers weren't the only ones concerned with how Marshall management seemed to be dealing with the Commission. In response, someone had anonymously sent many of them a letter outlining their own concerns. McDonald would be a recipient of this letter. This became known as the Apocalypse Letter. Dear Sir, I am deeply troubled by the Challenger tragedy and the events immediately preceding and following the loss. I am a senior manager at the Marshall Space Flight Center and answered as a member of the Marshall Space Flight Center Flight Readiness Review Board for all 25 shuttle launches. I have watched in despair as William R. Lucas, Marshall Space Flight Center director, has lied time and time again in national news conferences. I have watched in disbelief as he has engineered a cover-up of the Marshall Space Flight Center involvement. When I add this to the deep concerns that I and many other senior managers secretly shared preceding the launch relating to the management philosophy associated with determining flight readiness, my conscience tells me to speak out. The Marshall Space Flight Center is run by one man, William R. Lucas. His style of management can best be described as feudalistic. In his 10-year tenure as center director, he established a personal empire built on the good old boy principle. The only criterion for career advancement is total loyalty to this man. The loyalty to country, NASA, the space program means nothing. Many a highly skilled manager, scientist, or engineer has been buried in the organization because they underestimated the man's psychopathic reaction to dissent. In my own case, I have played the game. I have learned not to debate with him, not to argue, but to compliment and flatter him. We have learned that we must tell him he is right even though he is wrong in order to survive. Lucas is a classic Godfather mentality who corrupts the merit promotion system at Marshall Space Flight Center to hold total power over the careers of 3,000 people. In addition to violating the merit promotion system, an investigation would reveal a great many other abuses of power, such as using the government aircraft at his disposal for personal trips. Combine this institutional corruption and dishonesty with the usual faults of the government bureaucracy and one has a problem situation of immense proportions. Morale at the Marshall Center, even in the best of times, is very low. Those of us who know him are not really surprised that he would resort to a cover-up in order to preserve his power. There is no major decision which is made at Marshall Space Flight Center which Lucas does not approve personally. Everyone within the agency looks to this man concerning the readiness of the shuttle main engines, the external tank, and the solid rocket boosters because these systems are so complex. No one outside of the Marshall Space Flight Center and its contractors have an in-depth understanding of the systems. This man selected the contractors, selected the government managers, and in some cases the contractor managers, approved countless system and subsystem designs, and many other aspects of the system. To this day, he is still the final approval authority for the continuing stream of design changes to the SRB. No one man in NASA has been more involved in the development, testing, and certification of the SRBs than this one man. No one individual within NASA has done more to place his personal stamp on a piece of hardware than this one man. No one man in NASA has done more to so completely suppress dissent to further his own power than this man. Unfortunately, no one man can hope to make these types of multidisciplined decisions successfully. This man was the individual who okayed the Challenger SRBs for launch over the objections of Thiokol engineers who thought they were too cold. This man, more than any other individual at NASA, is singly responsible for this terrible loss and the deaths of 7 good men and women. Lucas couldn't care less. It is common knowledge among the senior management at Marshall Space Flight Center that his primary concern is simply to cover his tail. He engineered a 2-phase cover-up at the Marshall Space Flight Center. All data and people were locked into the Huntsville Operations and Support Center. Lucas personally ordered his senior management that no one at the center was to talk to the press without going through him first. The cause of the tragedy was generally known within a few hours on the same day it happened. Yet, under Phase 1 of the cover-up, information was to be withheld as long as possible, then fed to the press piecemeal. It was reasoned that the longer the information could be covered up, the better, as the course of world events would eventually tend to dilute the initial shock and public reaction. Some Marshall Space Flight Center officials privately indicated that they were praying for another hijacking or something similar to take the heat off. Once data could no longer be held back, Phase 2 would be to present as much highly technical data as possible, letting the situation in the general public's mind be diluted by various confusing theories which were sure to result. Stories were to be planted which would serve to shift blame away from Marshall Space Flight Center to Thiokol and the contractors doing the processing at the Cape. It has been apparent for some time that the flight readiness review process developed by Lucas and other senior NASA managers simply was not doing the job. It was not determining flight readiness. Rather, it established a political situation within NASA in which no center could come to the review and say that it was not ready. To do so would invite the question, if you are not ready, then why are you not doing your job? It is your job to be ready. At each flight readiness review, every center and every contractor are asked to vote on readiness. It is a no-win situation. For someone to get up and say that they are not ready is an indictment that they are not doing their job. As a consequence, the center gets up and basically snows headquarters with highly technical rationale that no one but the immediate experts involved can competently judge. Lucas has made it known that under no circumstances is the Marshall Center to be the cause for delaying a launch. Hence, Marshall Space Flight Center hardware is now flying with nozzles which have eroded to within 5 seconds of burn through in one case. No one to this date understands what caused the near catastrophe. Marshall Space Flight Center's Space Shuttle main engines are flying with potentially cracked turbine blades due to the same schedule and political pressures. If one of these blades were to come loose, it would be catastrophic. There are dozens of such problems which have been uncovered on these SRBs and the main engines and which none of the experts involved truly understand. Many of these have been glossed over simply because we were able to come up with a theoretical explanation which no one could disprove. We are flying shuttles based on the flawed management philosophy that if no one can prove the hardware will fail, then we will launch. And we vote. It is understood that Lucas expects his board to vote for launch. In the 25 center-level flight readiness reviews that I have participated, never has there been a single negative vote from a Marshall board member or a Marshall contractor that we are not ready. This amounts to hundreds of yeses and not a single no. This speaks for itself. This process is an exercise in self-disillusionment and illustrates the tremendous gap between Marshall Space Flight Center and NASA management decision-making and what happens in the real world. The contractors understand that Lucas can get them fired. Hence, they tell NASA what they know NASA and Marshall Space Flight Center want to hear. We are ready. And how many times has it been now that we have not been ready? We have had a main engine shut down milliseconds before the SRBs fired. Incidentally, one of these occurrences was never fully understood. We have had an abort to orbit. We have had numerous delays and numerous problems. And now we have had a catastrophe. Perhaps the most significant tragedy of this Orwellian nightmare that many of us find ourselves trapped within is what happened on the first launch this year. After many delays, we finally achieved a successful launch. However, but for the grace of God, we would have destroyed that shuttle and crew. To make a long story short, we experienced an anomaly and aborted launch for that day. In recycling the count, we discovered an undetected failure in which a sensor had broken off and prevented a valve from closing. Had we not experienced the other unrelated anomaly, we would have gone ahead with an undetected problem and blown up an engine which would have substantially blown up the external tank, destroying the vehicle and its crew. At the Challenger Flight Readiness Review, this problem was discussed and then dismissed. The Commission must look at this event as well. Something must be done here at the management level. Lucas should retire gracefully and a new manager brought in from the outside to reorganize the center. I know of no other way to deal with the good old boy mafia that has evolved over the time Lucas has ruled. Their ineptness and incompetence have contributed to this tragedy. I'm planning to retire soon and for obvious reasons do not plan to disclose my identity at this time. However, I have enclosed a copy of a presentation which Thiokol presented to Lucas in July of 1985, clearly outlining the problems with the seal. Nobody really understands the problem, and hence no one could disprove the theory. Lucas proceeded at risk rather than have the Marshall Space Flight Center delay the program. A classic management error in short-sightedness. God help us all. Apocalypse. The hearings would continue with the manager's testimony. It figures quite prominently in the discussion that you were quoted as saying, "Do you expect us to wait till April to launch?" Is that an accurate statement or not? It is certainly a statement that is out of context, and the way I read it was, quote, "My God, Thiokol, when do you want me to launch? Next April?" Mr. McDonald testified to another quote that says, "You guys are generating new launch commit criteria." Now both of those I think go together, and that's what I was saying. The total context, I think, in which those words may have been used is, there are currently no launch commit criteria for joint temperature. What you are proposing to do is generate a new launch commit criteria on the eve of launch after we have successfully flown with the existing launch commit criteria 24 previous times. With this LCC, i.e. do not launch with a temperature greater than 53 degrees, we may not be able to launch until next April. We need to consider this carefully before we jump to any conclusions. Maybe I misunderstood it. In any event, I thought the testimony was unclear about that, and I'm not sure that's all relevant who asked for it. It's pretty clear that you and Mr. Hardy were very unhappy about the recommendation of the engineers. As we understand it, the recommendation of the engineers was don't launch, and you expressed your displeasure. And somewhere along the line, they decided to have what seems like a 5-minute recess, which seemed very odd to me the first time I heard it. Why 5 minutes on a matter of such major importance? Why would anybody say, let's have a 5-minute recess? I would have thought they would have had a 5-hour recess on a matter of such major importance. Did you have any feeling or apprehension that a delay of the launch date for reasons related to the propulsion system would reflect on you or the Marshall organization? No, sir. My decision to proceed with the launch as recommended by the Thiokol official responsible for making such recommendations was based solely on the engineering data presented by Thiokol Engineering and the Marshall Engineering evaluation of those data. I can assure you, because I am absolutely certain, that no extraneous considerations such as schedule came into that decision process. At the completion of the caucus, of course, Mr. Kilminster came back on the loop and stated they had assessed all the data. I then asked Mr. Kilminster to send me a copy of his flight readiness rationale and recommendation. The conference was then terminated at approximately 11:15. I have no knowledge of, as has been testified, of Mr. McDonald being asked to sign that documentation. That would have been unusual because Mr. Kilminster signs all flight readiness documentation. Mr. Malloy, I want to let you finish, but let me tell you what troubles me very much. I see the charts and I have heard your presentations before, and I recognize your expertise and knowledge in this field. What is troubling, very seriously troubling, is if this is such a convincing matter to you, you are sure it's okay. How come then in a matter of such major importance, involving lives of 7 astronauts, you apparently were not able to convince any of the engineers at Thiokol who were working on this on a daily basis that you were right? Sir, I was not aware that they were not convinced. I had no knowledge of what went on in the 30-minute caucus at Thiokol, and when Mr. Reinhardt asked, are there any other comments, there were none. Now, would your opinion have changed if you had known all of the engineers, or substantially all of the engineers at Thiokol took another position and were opposed to the launch? Sir, I cannot speculate on what my decision would have been given certain other data. I'm not trying to put you on the spot, but we're checking on the particular process. We're checking on the decision-making process. Now in the process, we have the manufacturer or the engineers of the manufacturer who were working on this on a regular basis testifying that they were all against the launch. And we have testimony that management took over and made the decision contrary to the advice of the engineers. Now the question is, if you had known that, would it have made a difference? I presume if Mr. Bajali or Mr. Thompson or Mr. Lund said, look, we have a unanimous opinion here that it is unsafe to launch the 51L vehicle, that would have influenced, obviously, the decision that I would ultimately make. Leave out the word unanimously. Suppose it's 80% of the engineers. Wouldn't that have raised a major red flag to you? And wouldn't you have said to everybody around that this is a very serious matter? We have been concerned about the O-rings for a long time now, and we have a different weather condition, and we've never tried it at these temperatures. And the engineers, a lot of them are very worried. Wouldn't that have made a difference to you? Yes, sir. I think what I would have done in that case, I would have asked Mr. Kilminster how, in the light of that recommendation, he could recommend launching 51L, and I would have asked Mr. Hardy how he could concur in that. Following up on my question before, I want to point out testimony yesterday. The testimony yesterday was to the effect that at one point in the Thiokol discussion, Mr. Lund was told to take off your engineering hat and put on your management hat, because Lund at that point had disapproved the launch decision. So they said, take off your engineering hat and put on your management hat. And I asked, how do you explain the fact that you seemed to change your mind when you changed your hat? And Mr. Lund responded by blaming NASA's reversal of its launch readiness review policy. He says that NASA put him in that frame of mind, and that's why, because he couldn't prove absolutely that it wouldn't work, that he changed his vote. That is his testimony. Do you accept that testimony? I heard the testimony, sir. Again, I wasn't privy to the conversation where he was told to change from an engineering hat to a management hat. But as I stated earlier, I deny that I had any change of philosophy which says prove to me that you can't launch versus prove to me that you can. I was simply looking at the engineering data that were presented and the conclusion that was drawn from those data, and I found it not to be logical. I can't believe that there weren't lots of discussions about the effective temperature on the O-rings. No, you make it sound as if this was sort of a routine discussion about data, and you always have a free exchange of information about data and so forth. The thing that is different, it seems to me, about this, you had a positive recommendation of no launch. The chart showed that Thiokol recommended against launch. Do you remember any other occasion when the contractor recommended against launch and that you persuaded them that they were wrong and had them change their mind? No, sir. That is the part that's troublesome. And they said that yesterday, that they thought that you wanted them to change their minds. And that's why they had to rely on management. And they construed what you and Mr. Hardy said to mean that you wanted them to change their minds. They didn't construe it to mean you had a fair discussion about the data. They construed it to mean, just as Mr. Lund said, that's what he thought you wanted. And I guess what you're saying is that wasn't what you wanted. You just wanted an intellectual discussion about the data. Their main problem during all of this, the engineers' main problem, was that they felt they didn't have the data. They felt that their temperature data was inconclusive and that they were worried about it, but they didn't have the data to quantify what problems the temperature could cause. And that was one of the bases for the recommendation not to launch in the first place, was that they just simply felt that they didn't have the proof that it was safe. Did you think you had the proof? Did you think you had the database to show that it was safe at these temperatures? No, all I did was recite the data that we had available to us and ask that we consider that decision in the light of all that data. Could you go to the telefax and see what in the telefax satisfied you? Because the telefax said that the evidence was not conclusive. Demonstrated sealing threshold is 3 times greater than the 38 thousandths of an inch erosion experienced on 15. That's a fact. If the primary seal does not seat, the secondary seal will seat. That is pretty positive, isn't it? Yes, sir. Mr. Kilminster at Utah stated that he wanted to go off the loop to caucus for about 5 minutes. I believe at this point, Mr. McDonald, the senior Thiokol representative at Kennedy Space Center for this launch, suggested to Mr. Kilminster that he consider a point that I think I had made earlier, that the secondary O-ring is in the proper position to seal if blowby of the primary O-ring occurred. I clearly interpreted this as a somewhat positive statement of supporting rationale for launch. Personally, I believe any other interpretation of that is a case of convenience of memory. Could I interrupt because I think you did say something that was disturbing. When you referred to Mr. McDonald, you referred to convenience of memory, which suggested to me that you thought he was making something up for the record or some such. Was there anything that he said that you thought was not true? No, sir, I did not mean to imply that. Why did you use convenience of memory? That's what it sounded like. Well, I will explain that, and that may not be a good proper term to use. But there have been many of us that were involved in flight readiness issues for 51L, and I think there have been many of us that have gone back and asked ourselves questions and second-guessed ourselves. And I am not suggesting that anyone, and in any testimony before this committee or this commission, has knowingly in any way presented untruth. But I have talked to some of my colleagues, and I have found that they found it very difficult to remember precisely not only everything said and everything done, but even more than that, some of the motivations or some of the thoughts that took place at that time. Can I say, speaking for myself, that I respect your views and I believe what you just said. I also have the same feeling about Mr. McDonald, and I would like to have you withdraw those words, convenience of memory, because I don't think that's what he did. I would be pleased to do that. Mr. Hardy, going back to the process itself, the decision-making process, and I think that is vitally important because we have to make recommendations to the President about the future. And I think all of us feel that there have been a breakdown of sorts in the process. You said that you would not have approved of a launch if Thiokol had recommended against it. That is correct, isn't it? Yes, sir. Now suppose that Mr. Kilminster had said to you, I am sending the telefax, and this represents management's decision, and there are 3 or 4 of us, but that all the engineers are still opposed to the launch. How would you have reacted to that? I would not have accepted it. I have a little bit of trouble. This run-through of data that you're presenting in your analysis of it sounds like everything is copacetic, and yesterday I listened to these other fellows who showed great concerns. And it's hard for me to understand two different groups of engineering with the same data, one drawing a very great concern, a critical concern, and the other one being fairly relaxed. And that's why I keep asking the question of these two groups, who is the group that makes a recommendation to the decision makers? I'm still very confused on that. Let me just clarify that for you a little bit. The responsibility of myself and engineers that work in science and engineering is to review, assess, probe, and analyze the data that is put forth by the contractor engineering. And you draw a different conclusion than they draw? That is correct. So then, when they advise their management as to go or no go, it really isn't a very strong input. And when their management says go or no go, it may be a decision that doesn't have to be paid attention to. Well, as I was going to say, we have interface with that engineering department. We don't make recommendations to their management. Their engineering doesn't make recommendations to our management. Their engineering makes recommendations to the contractor management, and then we make recommendations to our project management. Now what the project manager is then assessing is the contractor's input to him and his civil service engineering input. That is what he ends up assessing. And I can tell you, if I were that guy, I would have a hell of a time knowing what to do. I don't know of many cases where he has just overridden or ignored the civil service engineering input that he has had. Then it gets back to the fact that the engineers at Thiokol who designed the thing, ran the tests, and did some interpreting of it are a non-entity. They don't count. Well, of course, to us the contractor is the entity. We don't cut the contractor up into departments. Mr. Reinhardt, during the caucus, didn't you have a discussion with Mr. McDonald where he voiced his strong opposition to the launch? At that point, I did not draw the conclusion, Mr. Chairman, that he was completely opposed to the launch, having made the statement that you should consider the secondary seal. Didn't he recommend at the time to you that the launch be delayed until late in the afternoon, until the temperatures reached 48 or 50? I'm not sure of that, Mr. Chairman. But you're not really trying to convince the Commission that you didn't know that Mr. McDonald had serious questions about the launch and didn't really want the launch to occur, are you? No, sir. I'm trying to relay what came across that evening during the discussion, Mr. Chairman. Martial elements in Huntsville and those elements at Kennedy Space Center, of course, as has been testified, had no knowledge of the internal Thiokol discussions during the 30 to 35-minute caucus that preceded their launch recommendation. Mr. McDonald, who had indicated, as you had stated, some concerns, as far as I know, did not take that opportunity to inject any of his thoughts or concerns via private telephone input into the internal Thiokol discussions that were going on during that caucus. As stated earlier, when I asked all the parties collectively if there were any disagreements with the final Thiokol recommendation that I received from Mr. Kilminster, there was no statement or comment from Mr. McDonald at that time sitting with Mr. Malloy and myself here at the Cape. And so your testimony is that after the decision was made, you were satisfied that Mr. McDonald had no questions in his mind, that he went along with the decision to launch? At the point, Mr. Chairman, when I asked very clearly and very deliberately on the telecon, while all parties were involved, I asked if there were any disagreements to all the parties, including Mr. McDonald, who was sitting right across from me, and there was no comment, no objection or anything raised at that time. I accept that, but later on didn't you know he continued to object and there was a lot of opposition on the part of the Thiokol people? I did not know of the lot of opposition of the Thiokol people. Mr. McDonald had the opportunity to inject anything into that Thiokol internal if he chose to. As far as I know, there was nothing constraining him. I had the Marshall engineering support of that activity, and I had the SRB manager's decision that he wanted to proceed, which I concurred with. And those were the inputs that I had that evening at that point in time. The Commission then asked the engineers about how they're going to redesign the field joint to be safer for future launches. I think one of the things that was missed is subscale testing is inadequate, and I know it's expensive to run full-scale tests with a gadget 12 feet in diameter and 100 feet long, but to continue without doing it, no matter what it costs, I think is a mistake. Who in Thiokol is working on the new design? Boisjoli, Russell, and Ebeling respond, I am. Do you all agree with the comment Mr. Sutter just made? Absolutely. That blow-by rig was a static rig, and it was never intended to show sealability of a joint. This was the 30 degree? Yes, it is, and it was never intended to show sealability. It was to show blow-by. It was put into the presentation that night because of a series of disjointed efforts under an umbrella by different people, trying to put together a presentation without a chance before presentation to go in and polish. If I had my druthers, I would have taken that thing out of there after the fact because it adds absolutely nothing to the presentation that night. Mr. McDonald, are you working on the new design? Part-time when I can. I've had some ideas that I've turned in on how to fix it. Has your assignment changed since the accident? Yes. What are you doing now? I used to be the director of the Solid Rocket Motor Project. I have a title now called Director of Special Projects. The people that all worked for me work for somebody else. I am involved in reviewing some of the failure data that is provided to me and coming up with some ideas on how to fix it, and define a test vehicle that will give us meaningful information, which is a full-scale hot-fire test. Were you given any reason for the change in assignment? Well, that is my second change in assignment since the hearing started. My first change after the 14th of February testimony in Florida, I was pulled out of my position and given the assignment of scheduling. Was any reason given? No reason other than this is what I was going to do, and my people again were put aside and assigned under somebody else, and I wasn't to be involved. Do you have any reason, Mr. McDonald, to think that you were given another assignment because of the testimony you gave before the commission? Yes, I do. I feel that I was set aside so that I would not have contact with the people from NASA again because they felt that I either couldn't work with them or it would be a situation that wouldn't be good for either party. And so I was taken out of the failure analysis work that I was doing at Huntsville prior to that assignment. So you were in effect punished for being right? I feel I was. Mr. Boisjoli, your assignment hasn't changed at all? In one respect, yes. In one respect, no. I have been designated as SEAL coordinator. I have been preparing a lot of information for input, but I too have been put on the sideline in that loop with relation to the customer. Do you feel that may be in retaliation for your testimony? I think that is a possibility, a distinct possibility. Does anybody from Thiokol want to comment on what Mr. McDonald or Mr. Boisjoli said? I'm Bob Ebeling. Prior to this effort, I was involved with the night of January 27th. The SEAL Task Force, to give you an instance, was under my auspices as a manager at that time prior to the incident, and since then, that SEAL Task Force has been dissolved and reorganized under a different manager. It is just one of the anomalies that has gone on since then, and I think it has got something to do with testifying. Well, having said all of that, you know what I'm driving at. I mean, if it appears that you're punishing the two people who are right about the decision and objected to the launch, and then they're demoted or they feel that they're being retaliated against, that is a very serious matter. It would seem to me, just speaking for myself, they should be promoted, not demoted or pushed aside. Do you want to comment on that? There was certainly no demotion involved that I know of. Well, you heard what Mr. McDonald said. I was not demoted. They just took my people away and gave me a more menial job as far as I was concerned. Alright, I'll withdraw the use of the word demoted. It sounds as if you were demoted. I felt like it. I want to make a comment to Mr. Kilminster, I guess, but to the company as a whole. I'm very upset about the testimony Mr. McDonald gave. It's a very serious matter. In this kind of an accident where people come before a commission and tell the truth and then they are treated as he believes he has been treated, which is obviously in some way punishment or retaliation for his testimony, it is extremely serious. And the whole idea of the program is to have an openness and to have an honest exchange of views. And in this case, Mr. McDonald and Mr. Boisjoli and the others, Mr. Thompson and the others, were right. If their warnings had been heeded that day and the flight had been delayed, there's no telling what would have happened. We might never have had the accident. And to have something happen to him that seems to be in the nature of punishment is shocking, and I just hope that you convey that to management. I don't know how the others feel, but that's how I feel. I would think you would want him in all of your discussions, and Mr. Boisjoli and he shouldn't be treated that way. He should be treated the other way, that he was right and you were wrong, and others who changed their decisions were wrong. And to have something that seems to be in the nature of punishment is very, very distressing, and I just wanted you to know that. Mr. McDonald, subsequent to the accident, in your testimony before this commission, did you receive any personal comment from people at NASA about your testimony? I'm not sure of the exact meeting. It was a 2-day meeting, and the second day I was there, Mr. Malloy came into my office and slammed the door, and as far as I was concerned, was very intimidating to me. He was obviously very disturbed and wanted to know what my motivation was, and I won't use his exact words, for doing what I was doing. And I asked him, what's his problem? Do you mean what my testimony was? And he said no. As I understand it, you're giving information to the commission without going through your own management, without going through NASA, and what's your motivation for doing that? And I told him to calm down, that I didn't think I had to get a note from my mother or anyone to give anybody information, and I felt it was appropriate to give them information. I had not gone through, I guess, the proper channels or something in doing that, and for some reason he was very upset about that and was very intimidating, but I ignored him. Did you get the feeling that they wanted to control this flow of information to the commission? I got the feeling that that was happening from things that I was reading, the data that I was looking at, and the conclusions that were drawn, and how they were drawn, instead of focusing it, to me was making it fuzzy. Mr. Malloy, do you have any comment to make on Mr. McDonald's statement? Yes, sir, if you would like for me to go and give you my version of that discussion. Why don't you? Yes, sir, I would be glad to. As often happens, I guess, when we have a meeting, we don't all remember it being the same. It must have been a different meeting. I came to Mr. McDonald's door and asked him if he had a moment, and he said he did, and I then closed the door. I didn't realize I slammed it. I was not upset. I think I started by shaking Al's hand and said, "Before I say anything, I want you to know that I don't have any personal feelings one way or the other about what has occurred subsequent to the launch. However, I have a curiosity, and the curiosity I have is why you have taken the approach that you have in circumventing your own management and the customer in voicing concerns about the launch of 51L that were never voiced to his management or me." His response to that was that he was very upset about the way the investigation was going at Marshall when he was down there. But the discussion that Mr. McDonald referred to was initiated by you? Yes, sir, it was. And what was the purpose of it again? And don't go through the whole thing, but what was the purpose? Why did you do it? Why I did it was based upon his testimony that he had objected to the launch and continued to protest the launch after the discussion on the night of the 27th when that was not a fact. In other words, you were challenging his veracity at this point? I wondered why he said that when he did not pass that on to his management, nor did he pass it on to me, nor did at any time during the launch process when he was on the console during that morning did he make any comments or continue to object to the launch. So you had no particular motive to start this discussion other than to satisfy your own curiosity? Yes, sir. Mr. McDonald, do you have something to tell us in which you presumably disagree in some way with the conclusions or the attitudes that we have been getting? Because we got most of our information directly from them and not directly from you, and I wanted to correct that if possible. If you had something to suggest about the way we interpret the results. And have you seen the kind of results that they have had? The conclusions from that presentation were that if you look at the conclusions, they don't even mention temperature in there at all. But even where they do mention temperature as having an effect, that by itself couldn't explain the problem. It had to be in conjunction with other things. Do you mean like the seal fitting into the groove? That is correct, and it is obviously, I think, biased towards potential assembly problems, either through the assembly itself or contamination of things that one can't specifically prove. Mr. McDonald, you testified that Malloy advised you about how you should convey information to the Commission? Well, he asked me why I was doing it, what I was doing, and why I was taking the liberty of giving information directly to the Commission without going through my own management and through NASA first. That is exactly what he asked me, and it wasn't in a nice voice. Well, will you feel free to give the Commission any information you want to give us, and if you consider what Mr. Malloy told you as a direction, forget it, because we are running this investigation, and you have access to us anytime you want, and that applies to all of you. Any instructions from Mr. Malloy about how the investigation was going to be conducted or how information was going to be conveyed was directly opposite what we told them. They all knew that, and I was very surprised to hear Mr. McDonald say that. Now, Mr. Malloy, I guess, says he didn't say that. From my vantage point, what I was talking about was not any information related to the investigation. My question was why, if he had those concerns, did he not express those concerns to his management on the night of the 27th or on the morning of the 28th? He said you questioned him about why he was giving information directly to the Commission and not going through NASA and his own management. Did you say that? Yes, sir. What I said was related to the events of the 27th. My question was, if he had all those concerns, why did he not relay those concerns to his management on the night of the 27th and up to the launch time on the 28th? Management was taking the position that the engineers failed their duties because if they truly believed that it was as serious of a concern as they were saying, they should have ignored the teleconferences and caucus and let higher-ups know about their concerns. This would have been an extremely unusual action and would not have guaranteed a delay. They wouldn't have any better data to hand to the administrators than had already been presented and thoroughly debated during the initial teleconferences. With this testimony, the hearings came to a close. The Commission would gather their findings and present it to the President and the public. Given the benefit of hindsight and an intense investigation, the Commission collects some findings of their own. Excerpts from the Rogers Commission read, "The history of problems with the solid rocket booster O-ring took an abrupt turn in January 1984 when an ominous trend began. Until that date, only one field joint O-ring anomaly had been found during the first 9 flights of the shuttle. Beginning with the 10th mission, however, and concluding with the 25th, the Challenger flight, more than half of the missions experienced field joint O-ring blowby or erosion of some kind. A likely cause of the O-ring erosion appears to have been the increased leak check pressure that caused hazardous blowholes in the zinc chromate putty. Zinc chromate putty is placed between the O-rings in the center of the booster. In the assembled configuration, the putty was intended to act as a thermal barrier to prevent direct contact of combustion gas with the O-rings. It was also intended that the O-rings be actuated and sealed by combustion gas pressure displacing the putty in the space between the motor segments. The displacement of the putty would act like a piston and compress the air ahead of the primary O-ring and force it into the gap between the tang and clevis. This process is known as pressure actuation of the O-ring seal. This pressure actuated sealing is required to occur very early during the solid rocket motor ignition transient because the gap between the tang and clevis increases as pressure loads are applied to the joint during ignition. Should pressure actuation be delayed to the extent that the gap has opened considerably, the possibility exists that the rocket's combustion gases will blow by the O-ring and damage or destroy the seals. Believing at the time that the zinc chromate putty could mask an O-ring's failure to seal during the leak check process, it was decided that the leak check pressure would be doubled from 100 psi to 200 psi from that point forward. Such holes at booster ignition from the increased leak check pressure provide a ready path for combustion gases directly to the O-ring. The blowholes were known to be created by the higher pressure used in the leak check. The significance of the possibility that putty could keep the motor pressure from promptly reaching the O-rings to pressure actuate and seal them was apparently not fully appreciated prior to the Challenger accident. During the investigation, it became evident that several variables may affect the putty performance and, in turn, seal performance. Test results demonstrated that putty performance as a pressure seal is highly variable. The results may be interpreted to indicate that the putty can maintain pressure during the ignition transient and prevent O-ring sealing. Clearly, the increased pressure used in the leak check increased the likelihood of a gas path through the putty to the primary seal. That is, with the increased pressure, blowholes in the putty are more likely with the resulting greater potential for erosion damage to the O-ring. On the positive side, the blowholes tend to prevent the delay in pressurization. This further illustrates the influence of putty variables on the performance of the solid rocket motor seals. It is possible that water got into some, if not all, STS-51L field joints. Subsequent to the Challenger accident, it was learned that water had been observed in the STS-9 joints during restacking operations following exposure to less rain than that experienced by STS-51L. It was reported that water had drained from the STS-9 joint when the pins were removed and that approximately half an inch of water was present in the clevis well. While on the pad for 38 days, STS-51L was exposed to approximately 7 inches of rain. Analysis and tests show that water will freeze under the environmental conditions experienced prior to the 51L launch and could unseat the secondary O-ring. During the process of freezing, ice would start by forming from the outside in the colder air. This would push the remaining water further up into the joint, closer to the secondary O-ring. If enough of this water froze, it could potentially unseat the secondary O-ring, placing both O-rings in the wrong position for launch. At launch, the boosters are subjected to forces which bend and twist them. These forces cause physical changes in the shape of the boosters, actually squashing them out of round and bending them along their entire length. The dynamic effects of this out of roundness are most significant just after booster ignition when the hold down bolts have been released, because in the previous 6.6 seconds, the boosters have actually been bent forward by the thrust from the main engines. The elastic energy stored in the entire system is then released, inducing a bending vibration in the boosters. This bending causes the case to change its shape from circular to elliptical. This deflection is a consequence of a vibration and occurs at a frequency of about 3 cycles per second. The dynamic effects cause an increase in the joint rotation and hence increase the gap between the tang and clevis by about 10%. Another dynamic load results from the geometry of the struts which attach the booster to the external tank. Strut P12 is attached to the booster at about the 314 degree point and imposes additional inertial forces on the booster which tend to additionally increase the gap by 10 to 21%. The diameters of the two solid rocket motor segments that failed on 51L had grown as a result of prior use. The growth resulted in a condition at the time of launch wherein the maximum gap between the tang and clevis in the region of the joint's O-rings was no more than 8 thousandths of an inch, and the average gap would have been 4 thousandths of an inch. With the tang to clevis gap of 4 thousandths of an inch, the O-ring in the joint would be compressed to the extent that it pressed against all 3 walls of the O-ring retaining channel. For pressure actuation to work most effectively, a space between the O-ring and its upstream channel wall should exist during pressurization. A tang to clevis gap of 4 thousandths of an inch, as probably existed in the failed joint, would have initially compressed the O-ring to the degree that no clearance existed between the O-ring and its channel. At the cold launch temperature experienced, it would remain in its compressed position in the O-ring channel. Thus, it is probable the O-ring would not be pressure actuated to seal the gap in time to preclude joint failure due to blow-by and erosion from hot combustion gases. The ambient temperature at time of launch was 36 degrees Fahrenheit, or 15 degrees lower than the next coldest previous launch. The temperature at the 300 degree position on the right aft field joint circumference was estimated to be 28 degrees plus or minus 5 degrees Fahrenheit. This was the coldest point on the joint. Temperature on the opposite side of the right solid rocket booster facing the sun was estimated to be about 50 degrees Fahrenheit. The STS-51L mission launched on January 28, 1986 at approximately 11:38 a.m. A series of puffs of smoke were observed emanating from the 51L aft field joint area of the right solid rocket booster after ignition. The puffs appeared at a frequency of about 3 puffs per second. This roughly matches the natural structural frequency of the solids at liftoff and is reflected in slight cyclic changes of the tank to clevis gap opening. This was a significant amount of blowby, and the dark black smoke is indicative that the O-rings themselves were being burned away. It is believed that the shuttle didn't immediately blow up on the launch pad because soot and debris from the motor firing had sealed the area between the now eroded O-rings and the walls of the booster. 51L left the launch pad in this incredibly dangerous situation. From this point onward to approximately 59 seconds, all systems appeared to perform within their design boundaries. At this point, the vehicle undergoes the strongest wind shear condition ever experienced by a shuttle launch up until that point. This was believed to have weakened the soot and debris sealing the eroded O-rings to the point that it could no longer hold back the pressure from the booster. At 58.8 seconds, a flame reappeared, emanating from the general region where the puff of smoke was observed near liftoff. Photographic analysis indicated that the plume breached the tank and produced a liquid hydrogen leak at 64.6 seconds. At 72.2 seconds, the guidance system showed that right SRB motion was not the same as the orbiter and left SRB, indicating that the lower external tank to SRB attachment strut was severed or pulled loose from the external tank. This is what initiated the explosion, and multiple events happened simultaneously from here. As the leaking exhaust has burned through the liquid hydrogen tank, it begins failing. As the liquid fuel is being stored under pressure, the entire rear dome of the liquid hydrogen tank gave out and broke free. The booster, now freed from its strut constraining itself to the lower portion of the external tank and still providing thrust, began to pivot around its remaining forward attach point. There was evidence that during the breakup sequence, the right solid rocket booster struck the outboard end of the orbiter's right wing and right outboard elevon. Since the internal pressure of the liquid hydrogen tank is at approximately 33 pounds per square inch, a sudden venting at the aft section produces a large initial thrust that tails off as the pressure drops. Due to this, the hydrogen tank would be propelled towards the intertank structure and liquid oxygen tank inside of the external tank structure. At the same time, the solid rocket booster collides with the intertank, the structure in the external tank between the liquid oxygen and hydrogen. That was immediately followed by total vehicle structural breakup and explosion at 73.2 seconds. As the solid rocket boosters had become visibly separated from the rest of the vehicle, the range safety officer intentionally detonates explosives placed on them to stop them from potentially ending in an area with bystanders. Debris from the explosion can be recognized from the footage. This one is the crew compartment. The crew module wreckage was found submerged in about 90 feet of ocean water concentrated in an area of about 20 feet by 80 feet. The definitive cause of death for the crew was looked into after the explosion. A report written by Joseph P. Kerwin, biomedical specialist from Johnson Space Center, outlines many of their findings. A team of engineers and scientists has analyzed the wreckage and all other available evidence in an attempt to determine the cause of death of the Challenger crew. The findings are inconclusive. The impact of the crew compartment with the ocean surface was so violent that evidence of damage occurring in the seconds which followed the explosion was masked. Our final conclusions are: the cause of death of the Challenger astronauts cannot be positively determined. The forces to which the crew were exposed during orbiter breakup were probably not sufficient to cause death or serious injury, and the crew possibly, but not certainly, lost consciousness in the seconds following orbiter breakup due to in-flight loss of crew module pressure. The forces on the orbiter at breakup were probably too low to cause death or serious injury to the crew, but were sufficient to separate the crew compartment from the forward fuselage, cargo bay, nose cone, and forward reaction control compartment. The forces applied to the orbiter to cause such destruction clearly exceed its design limits. The data available to estimate the magnitude and direction of those forces included ground photographs and measurements from onboard accelerometers, which were lost 0.2 of a second after vehicle breakup. Two independent assessments of these data produced very similar estimates. The largest acceleration pulse occurred as the orbiter forward fuselage separated and was rapidly pushed away from the external tank. It then pitched nose down and was decelerated rapidly by aerodynamic forces. There are uncertainties in our analysis. The actual breakup is not visible on photographs because the orbiter was hidden by the gaseous cloud surrounding the external tank. The range of most probable maximum accelerations is from 12 to 20 Gs in the vertical axis. These accelerations were quite brief. In 2 seconds, they were below 4 Gs. In less than 10 seconds, the crew compartment was essentially in freefall. Medical analysis indicates that these accelerations are survivable, and that the possibility of major injury to crew members is low. After vehicle breakup, the crew compartment continued its upward trajectory, peaking at an altitude of 65,000 feet approximately 25 seconds after breakup. It then descended, striking the ocean surface about 2 minutes and 45 seconds after breakup at a velocity of about 207 miles per hour. The forces imposed by this impact approximated 200 Gs, far in excess of the structural limits of the crew compartment or crew survivability levels. The separation of the crew compartment deprived the crew of orbiter-supplied oxygen, except for a few seconds supply in the lines. Each crew member's helmet was also connected to a personal egress air pack containing an emergency supply of breathing air, not oxygen, for ground egress emergencies, which must be manually activated to be available. 4 PEAPs were recovered, and there is evidence that 3 had been activated. The non-activated PEAP was identified as the commanders, one of the others as the pilots, and the remaining ones could not be associated with any crew member. The evidence indicates that the PEAPs were not activated due to water impact. It is possible but not certain that the crew lost consciousness due to an in-flight loss of crew module pressure. Data to support this is, the accident happened at 48,000 feet, and the crew cabin was at that altitude or higher for almost a minute. At that altitude, without an oxygen supply, loss of cabin pressure would have caused rapid loss of consciousness and it would not have been regained before water impact. PEAP activation could have been an instinctive response to unexpected loss of cabin pressure. If a leak developed in the crew compartment as a result of structural damage during or after the breakup, even if the PEAPs had been activated, the breathing air available would not have prevented rapid loss of consciousness. The crew seats and restraint harnesses showed patterns of failure, which demonstrates that all seats were in place and occupied at water impact with all harnesses locked. Impact damage was so severe that no positive evidence for or against in-flight pressure loss could be found. Finally, the skilled and dedicated efforts of the team from the Armed Forces Institute of Pathology and their expert consultants could not determine whether in-flight lack of oxygen occurred. Richard Feynman, being a character of his own, wanted to include his comments in an official addendum alongside the Commission's findings. Rogers, reading the comments Feynman wanted to add, asked him to remove his addendum or tone down most of the comments. Feynman subsequently refused to sign the Commission's report until his unedited comments were included. Rogers backed down and gave Feynman's comments his own section in the report, Appendix F, Personal Observations on the Reliability of the Shuttle. It appears that there are enormous differences of opinion as to the probability of a failure with loss of vehicle and of human life. The estimates range from roughly 1 in 100 to 1 in 100,000. The high figures come from the working engineers and the very low figures from management. What are the causes and consequences of this lack of agreement? Since 1 part in 100,000 would imply that one could put a shuttle up each day for 300 years expecting to lose only one, we could properly ask, what is the cause of management's fantastic faith in the machinery? We have also found that certification criteria used in flight readiness reviews often develop a gradually decreasing strictness. The argument that the same risk was flown before without failure is often accepted as an argument for the safety of accepting it again. Because of this, obvious weaknesses are accepted again and again, sometimes without a sufficiently serious attempt to remedy them, or to delay a flight because of their continued presence. It is true that if the probability of failure was as low as 1 in 100,000, it would take an inordinate number of tests to determine it. But if the real probability is not so small, flights would show troubles, near failures, and possible actual failures with a reasonable number of trials. In fact, previous NASA experience had shown, on occasion, just such difficulties, near accidents, giving warning that the probability of flight failure was not so very small. Why do we find such an enormous disparity between the management estimate and the judgment of the engineers? It would appear that, for whatever purpose, be it for internal or external consumption, the management of NASA exaggerates the reliability of its product to the point of fantasy. The phenomenon of accepting for flight seals that had shown erosion and blowby in previous flights is very clear. The Challenger flight is an excellent example. There are several references to flights that had gone before. The acceptance and success of these flights is taken as evidence of safety, but erosion and blow-by are not what the design expected. They are warnings that something is wrong. The equipment is not operating as expected, and therefore is a danger that it can operate with even wider deviations in this unexpected and not thoroughly understood way. The fact that this danger did not lead to a catastrophe before is no guarantee that it will not for the next time, unless it is completely understood. When playing Russian roulette, the fact that the first shot got off safely is little comfort for the next. The origin and consequences of the erosion and blow-by were not understood. They did not occur equally on all flights and all joints, sometimes more and sometimes less. In spite of these variations from case to case, officials behaved as if they understood it, giving apparently logical arguments to each other, often depending on the success of previous flights. For example, in determining if Flight 51L was safe to fly in the face of ring erosion in Flight 51C, it was noted that the erosion depth was only 1/3 of the radius. It had been noted in an experiment cutting the ring that cutting it as deep as 1 radius was necessary before the ring failed. Instead of being very concerned that variations of poorly understood conditions might reasonably create a deeper erosion this time, it was asserted there was a safety factor of 3. This is a strange use of the engineer's term, safety factor. If a bridge is built to withstand a certain load without the beams permanently deforming, cracking, or breaking, it may be designed for the materials used to actually stand up under 3 times the load. This safety factor is to allow for uncertain excesses of load, or unknown extra loads, or weaknesses in the material that might have unexpected flaws, etc. If now the expected load comes onto the new bridge and a crack appears in a beam, this is a failure of the design. There was no safety factor at all, even though the bridge did not actually collapse because the crack went only 1/3 of the way through the beam. The O-rings of the solid rocket boosters were not designed to erode. Erosion was a clue that something was wrong. There was no way, without full understanding, that one could have confidence that conditions the next time might not produce erosion 3 times more severe than the time before. Nevertheless, officials fooled themselves into thinking they had such understanding and confidence, in spite of the peculiar variations from case to case. During the flight of 51L, the 3 space shuttle main engines all worked perfectly, even at the last moment, beginning to shut down the engines as fuel supply began to fail. The question arises, however, as to whether, had it failed, and we were to investigate it in as much detail as we did the solid rocket booster, we would find a similar lack of attention to faults and a deteriorating reliability. In other words, were the organization weaknesses that contributed to the accident confined to the solid rocket booster sector, or were they a more general characteristic of NASA? To that end, the space shuttle main engines and the avionics were both investigated. A difficulty was found with certain temperature sensors sometimes failing. Yet 18 months later, the same sensors were still being used, still sometimes failing, until a launch had to be scrubbed because 2 of them failed at the same time. Even on a succeeding flight, this unreliable sensor was used again. Again, reaction control systems, the rocket jets used for reorienting and control in flight, are still somewhat unreliable. There is a considerable redundancy, but a long history of failures, none of which has yet been extensive enough to seriously affect flight. The action of the jets is checked by sensors, and if they fail to fire, the computers choose another jet to fire. If a reasonable launch schedule is to be maintained, engineering often cannot be done fast enough to keep up with the expectations of originally conservative certification criteria designed to guarantee a very safe vehicle. In these situations, subtly and often with apparently logical arguments, the criteria are altered so that flights may still be certified in time. They therefore fly in a relatively unsafe condition with a chance of failure of the order of 1%. It is difficult to be more accurate. Official management, on the other hand, claims to believe the probability of failure is 1,000 times less. One reason for this may be an attempt to assure the government of NASA perfection and success in order to ensure the supply of funds. The other may be that they sincerely believed it to be true, demonstrating an almost incredible lack of communication between themselves and their working engineers. In any event, this has had very unfortunate consequences, the most serious of which is to encourage ordinary citizens to fly in such a dangerous machine, as if it had attained the safety of an ordinary airliner. The astronauts, like test pilots, should know their risks, and we honor them for their courage. Who can doubt that McAuliffe was equally a person of great courage who is closer to an awareness of the true risk than NASA management would have us believe? Let us make recommendations to ensure that NASA officials deal in a world of reality and understanding technological weaknesses and imperfections well enough to be actively trying to eliminate them. They must live in reality and comparing the costs and utility of the shuttle to other methods of entering space. And they must be realistic in making contracts, in estimating costs, and the difficulty of the projects. Only realistic flight schedules should be proposed, schedules that have a reasonable chance of being met. If in this way the government would not support them, then so be it. NASA owes it to the citizens from whom it asks support to be frank, honest, and informative, so that these citizens can make the wisest decisions for their use of their limited resources. For a successful technology, reality must take precedence over public relations, for nature cannot be fooled. Somewhat controversially, criminal charges would never be brought against anyone for their part in launching 51L, with Chairman Rogers stating, "I don't believe there was any venality here. I don't believe there was gross negligence. I think there was a misunderstanding about what each person was responsible for. In the case of NASA, it's such a big organization with so many people that it has all the evils of bureaucracy. Responsibility is pretty diffuse. The Marshall people thought they had the right to make final decisions because they were level 3, while those at level 2 did not think that was the case. That was the mistake of the system. But in terms of criminal negligence, you could certainly say that the people at Marshall thought they had the right to close out this problem. They thought they had the right to decide it, and they decided it. And there were a lot of people involved in that decision. It wasn't just Larry Malloy. There were a lot of other people too. So I think it would be very difficult to prove the willfulness or even the gross negligence that is required for a criminal prosecution. Furthermore, I don't think it would be in the national interest." McDonnell's de facto demotion would not only catch the attention of the commission, but also politicians watching the hearings. In response, House Joint Resolution 634 was introduced. A joint resolution debarring Morton Thiokol Incorporated from contracting and subcontracting with NASA until a determination is made by the Comptroller General with respect to actions which were allegedly taken by such corporation against its employees because they gave certain information to the Presidential Commission on the Space Shuttle Challenger accident. Alan J. McDonald would be promoted onto the SRB redesign team. Over the span of 32 months, a new design would be manufactured and tested. Safety margins would be improved throughout the entire vehicle. The field joint would be redesigned, adding a capture feature and a third O-ring. This addition would help constrain the joint rotation, and if it did occur, the walls of the booster would push into the third O-ring, helping it seal. A heater would be added to each of the field joints on the launch pad, preventing the O-rings from ever getting colder than 75 degrees Fahrenheit. The entire space shuttle system would receive the same scrutiny in regards to safety as the boosters. Many design changes were made to improve the safety margins around the space shuttle main engines, external tank, and orbiter. The landing gears would have improved margins. Safety latches were added to prevent valves from accidentally closing, and the wings would be strengthened. The tile thermal protection system would be improved, which was known to take damage from launch. The flight readiness review process would be updated to help prevent a situation where one would need to prove that it would not be safe to launch. The redesigned solid rocket motor, or RSRM, would be tested to 6 times the amount that the original design was before the first shuttle launch. After their qualification, they would be ready for their next launch. As the investigation showed that NASA's planned launch schedule was unrealistic with work expectations, space shuttle missions would be dramatically scaled back following the Challenger accident. In contrast to the 9 missions that launched in 1985, only 2 space shuttle missions would take off in 1988, and 5 in 1989. The Vandenberg site was scrapped and never used for shuttle launches. Space Shuttle Endeavour would be built for Challenger's replacement. The scaling back of the Space Shuttle program missions caused the unconventional naming schema that the shuttle program had adopted to also become unnecessary. The shuttle program would return to simple numerical identification. The 26th Space Shuttle launch, or STS-26, would put all of these improvements to the test. STS-26 would be the first space shuttle launch with a crew composed of all space shuttle flight veterans. The mission would be piloted by Dick Covey, the man who spoke the final words to Challenger's crew.
Challenger, go at throttle up. Challenger, go at throttle up. Fido, trajectory. Go ahead. Trajectory, Fido.
STS-26 would lift off from Pad 39B on September 29, 1988, 975 days after the Challenger disaster. Space Shuttle Discovery's crew would orbit the Earth 64 times, completing all major scientific objectives, including the deployment of the TDRS-C satellite, the replacement for the communication satellite lost on 51L. STS-26 would land safely at Edwards Air Force Base 4 days, 1 hour, and 11 seconds after liftoff.
the gear down and lock. The report from Mission Control. Main gear touchdown. Commander out now, rotating the nose down, standing by for nose gear and touchdown.
The decision to launch Challenger under unsafe conditions cannot be pinned on one single individual decision or event. Placing all of the blame for the Challenger disaster on a few middle managers would indirectly absolve many others of the decisions that they had made that contributed to this event. Instead, the cause of the disaster was due to the much more insidious concept of normalized deviance. The decision to take a risk on a previous flight became the basis to continue as if nothing were wrong. Warnings about the field joints became an accepted part of launch rather than reason to halt the entire shuttle fleet until they were fixed. The decision to move forward with a knowingly flawed field joint design which opened upon firing instead of closing contributed significantly to this event. They thought blowholes through the zinc chromate putty designed to keep heat away from the O-rings was the source of the erosion they had observed. Given the weather in Florida at the Kennedy Space Center, thought was never given to the idea of an operational temperature constraint on the O-rings because they believed it would never even get cold enough to become an issue. Since it was considered not cold enough to become an issue, temperature trend data was never gathered, which would have clearly shown field joint distress and temperature are heavily correlated. This graph shows all of the flights with observed field joint distress. This was the data that the engineers were presenting to management to convince them that temperature was causing the field joint distress. It would be difficult to convince someone that temperature and field joint distress are correlated with this graph. Now, let's add all the flights, including the ones that didn't show any field joint distress or blowby. The correlation between temperature and field joint performance become immediately apparent. Without this chart, it left the engineers at Thiokol in a very weak position to support their arguments to delay. There are few events throughout the history of the world in which people remember exactly where they were and what they were doing when it happened. The Challenger disaster has been cemented into this list so conclusively that it is brought up as one of the main examples of this phenomenon. The Challenger disaster became a case study in management and engineering ethics, as well as the danger of working with unknowns. For many of the children watching the broadcast, it would be the first time that they would be introduced to the concept of death. This event remains a permanent reminder of the true dangers and risks that are inherent in human spaceflight. Now it's our job to make sure that this event and its painful lessons are never forgotten.
Mr. McAuliffe, the New Hampshire school teacher, came last. Funeral plans are being kept private. In a tribute to the 7, a sign read, "Challenger crew, we bid you farewell."
As the Challenger investigation continues, key personnel changes are made at NASA. The top managers who disregarded expert objections and decided to launch the shuttle leave NASA or are reassigned. At Morton Thiokol, the 4 vice presidents who failed to heed their engineers' warnings retire or are reassigned. The Rogers Commission report, released in June 1986, identifies the failure of the solid rocket booster seals, the O-rings, as the primary cause of the Challenger.
An anomaly noted on the SRM was the loss of a few pieces of cork insulation that ran down along the side of the case. In any other rocket system, this would not be of concern because the heater cables were inoperative at time of launch. However, the space shuttle was very sensitive to sources of debris during ascent that could potentially impact the wing and delicate thermal tiles on the orbiter. This had become a very serious issue on STS-26 when Discovery landed at Edwards Air Force Base in California. The damage to the thermal tiles on Discovery was very extensive and severe, the worst condition of any orbiter ever flown in the shuttle program. Naturally, we immediately put together a task force to determine if the cork on the RSRM had come off at splashdown or in flight, and how to prevent losing cork insulation on future flights. The ecstasy of returning the shuttle to safe flight quickly dissipated. We were back in the soup again, solving a potentially new life-threatening problem. As far as the loss of external insulation was concerned, we noted several areas where small pieces of cork were missing. Based upon detailed examination of the failed cork surfaces, we believe that most of the cork had been lost at water impact. However, the largest piece of cork, located in the area of the forward field joint, apparently had come off sometime during powered flight. We based this conclusion on our observation of soot, which indicated that the surfaces had been subjected to aerodynamic heating during booster burn. Inspection of the cork adhesive that was still attached to the case indicated several large voids where the cork was lost. Tap testing and ultrasonic inspection of the remaining cork also indicated several large areas of voids in the adhesive, apparently caused by trapped air during cork installation and closeout. We recommended ultrasonically inspecting the cork on STS-27 and filling all of the voids with an epoxy adhesive from a hypodermic needle. I was absolutely shocked at what I had learned from Rockwell on the orbiter. Its engineers revealed that the orbiter had experienced severe damage to its thermal protection tiles, and that one area on the orbiter wing had experienced such severe damage during ascent that the tile had eroded during re-entry down nearly to the wing's aluminum structure. This severe area of damage was of great concern because it had come very close to damaging the structural integrity of the wing, a problem that would have resulted in catastrophic failure of the orbiter during re-entry. Rockwell had carefully analyzed the problem and concluded that the damage to the tile had occurred early on ascent as a result of loss of external cork insulation from the solid rocket motors during their burn. After running numerous computer simulations, Rockwell engineers had concluded that the size and pattern of the damaged thermal tiles matched the location, size, and weight of the largest piece of cork lost on the RSRM in the area of the forward field joint on the right-hand SRB. Rockwell concluded that we were very lucky on STS-26 Discovery because it wouldn't have taken much more damage to destroy the vehicle during re-entry. Rockwell's analysis also showed that we were lucky that it was Discovery that was flying and not one of the other orbiters in the fleet, because its wing surface roughness, though significant, was considerably less than that of one of the other orbiters. If this vehicle this time had been Columbia, it most likely would have experienced a burn-through of the left wing and suffered a catastrophic re-entry.